Okay, start. A very good morning, everyone. Welcome to the last day of the discussion meeting on basic sciences. We have a short scientific program today with 2 sessions and 5 speakers. We expect to be finished with the talks as well as a valedictory ceremony before lunch. I would like to make a couple of announcements before we proceed. Post-lunch, we have the BRC visit. The transport for this is arranged at Training School Hostel at 2:30 p.m. If anyone from TMC or ACTRAC need a place to keep their phones or electronic gadgets, please approach Professor Maity. For the ACTRAC visit tomorrow, the transport leaves from Training School Hostel at 9 a.m. And all the pen drives containing all the talks are available at the help desk for collection. Finally, if you have missed any of the previous talks, please visit the YouTube link. Moving on. To begin the first session of today, I invite Professor Shashank Chaturvedi, Director of Institute of Plasma Research, to the stage. Please join me in welcoming him to chair the session.
Thank you. Today's first speaker will be Dr. S.K. Majumder from RRCAT. Please.
Good morning, everybody. To start with, today I will be presenting R&D activities at RRCAT in the area of physical sciences. I will give a brief overview. But before I start, I would like to thank Professor Vasudeva Rao, Honorable Vice-Chancellor of HBNI, for considering this kind of wonderful idea and meet, which was not held before. And I would like to thank Professor Maity and Professor Naik for inviting me here. So Before I start, let me tell you about the institute I represent. Everybody knows that Raja Ramanna Center for Advanced Technology. It is a unit of Department of Atomic Energy and engage in frontline non-nuclear research areas, laser particle accelerators and related technologies. The motto of RRCAT is photons in the service of mankind. And we have particle accelerators, indigenously designed, developed, and commissioned 2 synchrotron radiation sources, Indus 1 and Indus 2, serving as a national facility. As you know, that Indus 1 is a 450 MeV 125 milliampere electron storage ring, emitting radiation from mid-infrared to soft X-ray with a critical wavelength of 61 angstrom. Indus 2 is a 2.5 GeV 200 milliampere electron storage ring designed for production of X-rays. And we have another dedicated things on lasers activity is in the development of variety of laser systems and their utilization for application in industry, medicine, and research. So I will be giving a glimpse of the facilities which we have at RRCAT. I will be covering these topics, beam lines of synchrotron radiation sources. Then we have infrared free electron laser. We have pulsed high power lasers, atom trapping and cooling, then fiber Bragg rating based sensors and LIGO gravitational wave network. And lastly, I will be talking on biophotonics, which is my area of research in a little bit detail as advised by Dr. Maity. So I have already told that Indus 1 and Indus 2 are indigenously developed synchrotron. You are familiar with Professor Paul's talk yesterday. So it is being 24/7 operational since February 2010. And now people use several beam lines. So what is a beam line? Let me tell you this thing. The emitted radiation, that synchrotron radiation, is collected, collimated, and monochromatized and used for experiments. This complete instrumentation is called beam line. Okay, so that is the thing. And there are several beam lines. Some of them are operational. For example, the Indus 2, Indus 1 has 7 operational beam lines, and Indus 2 has 17 operational beam lines. And these are the, for example, beam lines run by RRCAT, and these red ones are run by BARC per se. So, so experimental techniques developed around the beam lines are like these. You can have structure determination using synchrotron-based X-ray, diffraction-based structural studies of materials and different conditions, determine structures of BRID interfaces, strain-stress determination, elemental composition of materials, and electronic structure of materials using photoelectron spectroscopy, chemical state, and near-neighbor structure by X-ray absorption spectroscopy. These are possible with the RRCAT beam lines, and people from all over the country, from different universities and institutes, they regularly use these beam lines, and HBNI students are using these beam lines for their PhD experiments. And these are the beam lines already have been discussed by BRC beam lines, and they use these beam lines for experiments. Some important beam lines, just a glimpse to let you know about the complexity of the beam lines. Already Dr. Paul has covered these beam lines. I will skip this thing just to show you that these are the various beam lines, and which are engineering application beam line, soft X-ray reflectivity beam line, BL03 we call it, and then X-ray lithography beam line, and these are the parameters, 4 keV to 25 keV energy range. Then angle resolved photoelectron spectroscopy beamline BL10, energy range 30 electron volt to 1000 electron volt. So these are the parameters. Then angle dispersive XRD BL12 beamline, this is very important beamline, and X-ray fluorescence microprobe BL16. So these are the several beamlines. So so these are, I am not going to the details of these things. So to sum up, activities around synchrotron sources are beam lines, which design development and then provide the beam lines to users as national facilities, and then technologies related to beamline instrumentation and development, and expertise on beamline related techniques, and research around utilization of beamline facilities, material science, electron microscopy, and microfabrication, MEMS, etc. But here I would like to mention about this thing that RRCAT has already been considered for developing the 4th generation synchrotron radiation sources. We call it Indus 3, so which will be sanctioned very soon. So it will have several experimentation and several activities will be around this activity, this industry. Now, let me talk about infrared free electron laser at RRCAT. This is the first of its kind in the country. So we have recently, this free electron laser has been made operational, and wavelength is around 12.5 to 50 micron, and electron beam energy is 15 to 25 MeV. Peak IR power is 4 megawatt in 10 picosecond pulses, and CW average at 30 milliwatt. So this is these parameters, and this is the infrared electron laser facility. And these are the experiments which can be done. IR terahertz spectroscopy facilities, so you can do frequency domain spectroscopy using IR sources and also lab-based sources, additional lab-based sources. Then time domain terahertz spectroscopy, and then complementary facilities to study low energy excitations, measurement of heat capacity, thermal and electrical conductivity, magnetization. All these things can be done using this facility. And already the experiments have been started, and HBNI student is using this facility, and other researchers as well. And there are other things, studies which are possible in future, that is frequency domain IR terahertz spectroscopy, then terahertz time domain spectroscopy. All these things are possible using this infrared free electron laser facility at RRCAT. Now let me talk about the other facility that is related to this laser, that is pulse high power ultra short lasers at RRCAT. This is basically Ti-Sapphire laser emitting at 800 nanometer. So we have started with 10 terawatt 45 femtosecond laser, and then we have 150 terawatt 25 femtosecond laser, and then recently 1 petawatt laser. The system has recently been installed. So these facilities are very powerful facilities, and they are basically, you can do lots of experiments, and there is a concept of tabletop electron laser. So very compact laser and parallel to synchrotron radiation sources like. So let me tell you a little bit in detail that what is the underlying principle, how it has been possible. It has been possible because of this famous discovery. You know that Donna Strickland and Gerard Moru got the Nobel Prize in 2018 for sharp pulse amplification for proposing this idea. So what is done is this laser pulse from a remote-locked femtosecond pulse is basically stretched temporally and also spectrally, and a series of amplifiers it gets amplified and then again compressed. So you get high peak power, this thing. So that led to the development of compact multi-terawatt and petawatt laser systems. And terawatt to petawatt pulse duration of 25 to 150 femtoseconds are possible. And possibilities of exawatt and zettawatt are also being explored. Today, people are reporting these things. And focus laser intensity right now achievable is 10 to the power up to 20 watt per centimeter square. People are targeting more than 10 to the power 23 watt per centimeter squares. So this is basically led to this, that with this ultra-short laser, why I told that compact low-cost particle accelerators are possible, because you know that when this laser beam you place or you shine on a gas that is a underdense gas target, so that is millimeter to centimeters in length, then you generate wake field acceleration. And that wake field acceleration, that electrons have very, very high energy which is coming out. Essentially, you shine this laser beam, and then from here, this side, you get high energy electron beams. So that is why you can get few MeV to several GeV thing, and X-ray generation laser synchrotron source, that's what it is called. So this is electron acceleration, and similarly, if the target is a solid target, that is high dense target, then a few microns thick, then you can generate these hot electrons, and then ion acceleration is possible because these electrons left behind a series of this set of positive ions, and then the field generated with this laser, very high electric field, that basically accelerates these ions, and this ion acceleration is possible. So people are, this group is doing experiments with this proton ion acceleration, and 1 to 50 MeV electron, this thing is possible, energy is possible. Now, application is particle acceleration, X-ray generation, particle diagnostics, X-ray diagnostics. This is laser plasma interaction possible. Then PIC simulations are people are doing, and pulse metrology of ultra-fast lasers. All these pulse duration, contrast, all these experiments are possible, and people are doing it. Now I come to the unique facility of atom pooling as run by here, Professor Sutra Mishra is here. So his activity it is. So it is, you can do basic science studies, Bose-Einstein condensation of rubidium atoms he has demonstrated, and electromagnetic induced transparency, RF traps for manipulation of atoms, high resolution spectroscopy, and then quantum sensors and devices. That is the most attractive field of research, cooling and trapping of atoms on atom chip, cold atom gravimeter, cold atoms, UHB sensor, all these things they are now doing. And just to have a glimpse of the complexity, so this is the experimental system which has been developed for atom trapping here. And you basically initial atoms are in a vapor form at room temperature, laser cooling in magneto-optical trap, followed by RF-induced evaporative cooling in magnetic trap, reached a very low temperature to reach Bose-Einstein condensation of atoms. So the final temperature of the cloud of rubidium atoms is 440 nanokelvin, and with this kind of Bose condensate, 16^5 Bose condensate. So this they have achieved already. And experimental facilities around this atom trapping and cooling, high resolution atomic spectroscopy, quantum optics, use of cold atoms in atomic interferometry and quantum information, design of various kinds of atom traps using lasers, static magnetic fields and RF fields, and work for cold atom-based quantum sensors. All these things are going on. Now, there is another important activity is, or facility is fiber Bragg grating. So research and development on fiber Bragg grating facility. So we have these parameters of RRCAT has developed this fiber Bragg grating facility, and they are basically being used for several experiments, and or that can be used for several experiments and analysis of fiber Bragg grating based high temperature sensor. This is possible. Currently, ABG-based high-temperature sensor development is an active area of research. And as a primitive type 1 FBG are mainly suitable for reliable temperature measurement only up to 300 degrees centigrade. The main challenge is, that high temperature sensors of ABG-based sensors which can sense high temperatures around 100 degree, 1000 degree centigrade or so. So challenges are there. So they are working on these things. So this FBG sensor temperature is very much useful for various applications. Even in nuclear environment, harsh environment, this can be done. Then theoretical and experimental studies on strength sensitivity enhancement of FBG. This is the study, future study, this study which can be done. So there are several things which you can do, like studies on different structures, analysis of strength transfer, enhancing the strength transfer coefficient, enhancement of strength sensitivity, like that. And studies on fiber grating based chemical sensors are also being pursued in RRCAT. Now, these are the some of the things ABG-based sensors have been already being used by VRC, Tarapur, then Indus One, Bimline, and then one company at Bangalore. They have been interested in using these things for strain measurement in railway track. And so they have been given these things, ABG sensors mounted on brake level for brake force measurement. So there are several applications like distributed temperature monitoring systems for laser tube in high vacuum. So all these things have been possible, and they're routinely doing it there. So other experiments, as I mentioned already, that can be done. Now I come to the LIGO gravitational work network. Gravitational network. So already you have Hanford and then Livingstone, and then this is the LIGO India, which will be coming up in Hingoli, Maharashtra. So this is the conceptual aerial view. So you have this LIGO India project. Proposal is for the construction of an advanced interferometric gravitational wave detector in India called LIGO India under an international collaboration with Laser Interferometer Gravitational Wave Observatory LIGO, USA. The 4 lead institutes, IUCAR, DCSM, IPR, and RRCAT USA will work together in realizing the Indian node of the International Gravitational Wave Detector Network in India. So that is there, and this is the optical layout. You have a basically microsensor interferometer with 4 kilometer by 4 kilometer this length, and there are several technologies which need to be developed for successful doing of these things, and these are the basically possible R&D activities around LIGO. So the most important thing is that LIGO detector science and technology, where ultra narrow line with laser system and squeeze light source development is one of the challenging tasks. Ultra high precision optics, that is for fabrication and metrology, large data set handling, thermal noise interferometer for optical coating characterization, suspension and isolation systems for vibration control and earthquake techniques, and RRCAT is already building 10-meter prototype interferometer experiments and cryogenic upgrades, and Pathfinder for Dragonfly project, remote telescope control, and large data handling. So these are the things. Now I come to the biophotonics, the last topic, which I will, since our group has been working in biophotonics, let me tell you that ours is a very multidisciplinary group. We have physicists, biologists, chemists, engineers, and we closely work with doctors. So this is largely governed by physics principles, physical science principles, biophotonics research. So our important mandate is, one of the important mandates is biomedical diagnosis. So we use fluorescence, diffuse reflectance, Raman spectroscopy. Then we have developed several these systems, optical coherence tomography for imaging, and then optical tweezers and micromanipulation. So we have developed various optical tweezers, and we do several experiments using that thing. We have those facilities. So we work on intact biological tissues, cells, and body fluids. So we have started this activity from mid-90s, and these have resulted in several, deliverables, and those have been technology transferred. For example, this is oncodiagnoscope. This is for oral cancer screening, and this is being used across the country in different hospitals in Tata Memorial. For example, Tata Memorial Hospital, Mumbai, Homi Bhabha Cancer Hospital, Sangrur, Varanasi, and several other hospitals in the country. And we regularly do cancer screening using this device with the help of oncologists. So then Raman probe, then this is OncoVision, and then tuberculoscope. So these are some of the technologies which have been transferred, and they have been manufactured and are being used by the doctors. So a basic hypothesis is that optical spectroscopy and imaging can improve diagnosis and therefore treatment of pathologic conditions. So basically light source, shine light, and the light either elastically, inelastically scattered. You analyze this thing, then that bears the disease information. That is the basic concept. So major attraction because it can give you real-time, non-invasive detection with morphologic and biochemic information, which conventional techniques fail to do right now. So basically, there are, there are 3 generic spectroscopic techniques: reflectance, fluorescence, and Raman scattering. So basically, elastic scattering is a phenomena by virtue of which we are able to see each other. You light falling on you, reaching my eye, I am seeing you as you are, and vice versa. So that means light scattered from your body is having the information, morphological information about you. So, but by looking at you, I cannot make out your biochemical makeup. So for that, I have to use inelastic scattering of light, either fluorescence or Raman. So all these things we have developed, these best techniques we have, technique-based systems we have developed. But let me tell you, I will discuss on only 2 important things, that is depth-sensitive optical spectroscopy and optical tweezer here because of lack of time. Conventional optical spectroscopy, which you are familiar with, has major limitation because you know that tissue is a layered medium. You know that it has dermal, epidermal layers, different layers of tissue. So what is happening, you know that in conventional spectroscopy, when you shine light on these things, you get a volume integrated signal. Your signals from different layers get mixed up, and you don't have any specific information from a specific layer. So that is the problem. So information sort is obscured. Okay, so that's why you need to have depth sensitive spectroscopic techniques. So there are, or optical techniques. So there are several things which are possible, as you know, the confocal, then coherence gating of optical coherence tomography. That work, this confocal, as you know, that it works best for non-turbid samples. Tissue is a turbid medium, so tissue has problems. Applicable or biological systems. And this coherence gating applicable only with some compromised turbid samples you can do, but when tissue-like media, then source detector separation, polarization gating, time gating, these are the techniques. So I will be talking on confocal and source detector separation here. As you know that confocal, in confocal Raman spectroscopy, what happens that, you know that confocal means you are mapping this point onto the detector point. So you have a pinhole which is allowing it to do so. So what is happening, you just focus it at different layers and you get the corresponding signal there. Sorry. So corresponding signals, you get it there. So that way you can probe different depths, because these out of focus photons will be rejected by the pinhole aperture here. But this confocal Raman in turbid media like tissue has problems. Basically, this axial spread of the excitation beam increases with depth. You know that you are focusing, and then this axial spread, because of multiple scattering, it increases. So you have poorer axial resolution. That's why. Then another thing is considerable out of focus photons are there, so you have that leads to poorer depth selectivity. Another practical problem is that when you do it, that the sample on the sample side, you are basically moving the objective, then sample touches the objective lens. If you cannot, that limits also, practically limits, and cannot probe deeper. That is 300 to 400 micron maximum you can go with this confocal. Now, up to what depth one can probe with confocal, and what is the problem? This I have this incident photons, you know that most of the photons, you know that they are multiple scattered, and very few photons are transmitted. That is called ballistic photons, and some photons undergo minimal scattering, snake photons. So this multiple scattering basically dominates, and that's why that limits the confocal fluorescence spectroscopy to probe deeper. So so depth sensitivity is lost, and SNR also degrades with depth. So that is the thing. So we proposed recently that off confocal Raman detection. This is the proposition, and So what we did in off confocal detection is that you have a confocal Raman configuration, but instead of moving this side, you move this detector pinhole here. Okay, so if you move away from the focal spot, in both sides you get the photons from the depth. So this is what we have proposed, and probing, we could get the probing depth of 800 micron up to that. So, and we have developed a handheld upconfocal Raman spectroscopy probe, which we use for, you know, that this is very useful. Say, for example, if you have this in a bottle, some liquid, say, for example, some liquid you do not know, it is water-like liquid. We can tell with the help of this probe what is the liquid there. So we regularly do experiments. For several experiments, we have shown that one of our activities is that food adulteration. So milk adulteration, so packaged milk in Amul milk or something. So if they are adulterated, say for example, urea is there or some other chemicals is there, melamine is there, you can use this probe and you can record Raman spectra and can tell. So this has been for that we are working on these things. Now, question is how to probe deeper, even beyond that. Say, for example, so solution is source detector separation. So principle is that, let me tell you graphically. So you shine this laser here, the laser is incident here, and you know that tissue is a turbid medium, means these photons are scattered by the different particles like cells, subcellular organisms like that, and you know that if you detect away from the your incidence point, so you can probe deeper photons, deeper moving photons. So that subsurface probing is based on the diffused component of the generated light. So that is the principle we use, and this is the implementation. There are two ways of implementing it. Either you have this kind of probes at probe-based thing, optical fiber-based thing. that you have in one side, you put this incident and several axially separated or spatially separated fibers you put to detect the emitted Raman light. And other thing is that you can have a circular illumination and the central collection. So this is called inverse spatially offset Raman spectroscopy. This technique is called spatially offset Raman spectroscopy. So all these things we have done or we have been doing, and we have proposed these things in SORS for detecting low Raman active target sample placed inside a highly Raman active diffusely scattering matrix. So say for example, if your plastic is highly Raman active, and if you have some low Raman active thing hidden in some plastic, so you can really do with this technique. So we have developed this portable system for inverse SORS, which we are using for in field for doing experiments on using Raman spectroscopy. Now I will come to the second topic which I have decided to talk about is optical tweezers. You know that Professor Arthur Askin got Nobel Prize in 2018, okay, for this. So we have developed several optical tweezer-based things. So Arthur Askin thought through his theoretical calculation, first realized that optical forces can be significant for microscopic objects like biological cells, and that gave the birth of optical tweezers. So this is a very powerful tool for manipulation of microscopic objects using microscopic using live cells. For example, you can with the help of these lasers, you can catch hold of a single cell. You know that single cell is of the dimension of around 20 micron. So you can catch hold of a cell without really touching it. So we have developed this thing. Let me, before going to that, let me tell you that the force exerted by this light, they are of two types, attractive and repulsive. You know that attractive force is called gradient force, which pulls the thing, pulls the object towards the focus, and the scattering force, that is, if you shine laser beam, then that force of light basically pushes the particle away from it. So there are two things. Okay. Now, understanding from ray optics, if we just take a simple look, then what happens? Say for example, this is light is falling, and this is the change in momentum of a photon on reflection. That gives rise to scattering force. So say for example, light beam is falling here, it is being reflected. Now this is the initial momentum, this is the final momentum. Now let us see the change in momentum. Okay, delta P. Okay, so delta P is in this direction. And then you have from Newton's third law, there will be an opposite force in this direction. Similarly for this, there will be this kind of thing. And you see that scattering force, this resultant force is here, and scattering force will push the object from, this is the laser beam coming from this side, and it will push the object from away from the laser beam. So that is the scattering force, and when the light is getting reflected, that scattering force dominates. Now let us think about another thing, that gradient force, change in momentum of a photon on refraction. What happens? Let us see. So light beam falling on these things, refracted, and then this is a change in momentum. Okay, and see, similar to the earlier thing, here you have this thing. So you see that the force direction is this thing, and resultant force basically is this side, grad, and this particle is pushed towards the focus. So this is what is understanding from ray optics. So force is nothing but the gradient of intensity is proportional to that. So objects feel a force toward the focus. That is the actual gradient force. And so stable optical trapping is possible, just 2 minutes. Optical trapping is possible only when gradient force is greater than scattering force. So if the gradient force is more than scattering force, there is always a tug of war. So they pull the object towards the focus. That is the basic principle of optical trapping. Okay, so we have developed several optical tweezers setup. So this is a schematic. So it is very simple setup. So these are the parameters. Okay. So, and several experiments, I will give you some glimpse of it. You can do a lot of playing around with optical trapping. We have done it. With the help of this optical trapping, normally what happens, you know, that you can rotate the object. So this is the rotation. So this is a malaria diagnosis. One thing is there. So basically malaria affected parasite. or parasite affected RBCs, they move slower as compared to normal RBCs under the optical trapping condition. And this was mentioned in Arthur Askin's Nobel lecture. And he told that, let me tell you the paragraph he told, that I am told that one Indian group has shown this use of optical trapping for malaria diagnosis. And when I say Indian group, it is not American Indian, it is Indian Indian. So he has told these things in Arthur Askin. So this is the thing which we have been doing, and several other things, optical gun, we have patented it, and intracellular transport, that is allotted tensor plant cells, several experiments we have done. And another thing has that optical trapping we have coupled with optical spectroscopy for single cell spectroscopy, okay? So that is facility is there. So we have done non-resonant Raman spectroscopy along with resonant Raman spectroscopy, and we have studied on, that effects of mobile phone emissions on RBCs, and change in hemoglobin oxygen affinity, effects of acute hypoxia oxygen affinity, red blood cells, all single cell level we have studied a lot of things, and a lot of works can be done even now. So now one important thing was that, is it possible, this is with the help of optical trap, as you are saying, it is possible to only hold dielectric particles. So our question was that whether metal nanoparticles can be trapped. Normally, that metal has free electrons, and the skin depth, that the skin depth basically is, we have seen that when the skin depth is greater than the dimension of the particle, that is a nanoparticle here, it is skin depth is greater, that's why nanoparticle is possible. But microparticle, metal nanoparticle, you cannot have, because scattering force will dominate there. So trapping is possible, and when we saw, and then we proposed this nano trap enhanced Raman spectroscopy technique, combining the principle of optical trapping, dry coating deposition Raman spectroscopy, and ACRS, that is surface enhanced Raman spectroscopy. These three things we have combined, and we have shown that with the help of this NT-ERS, we can have signal enhancement much higher compared to ACRS. Okay, so I will skip this thing. So that is what we have shown. So roughly, this is a glimpse of what we have at RRCAT. So before I end, I would really like to acknowledge our group directors from where, and division heads, section heads, and lab heads from where I have got the transparencies and have fruitful discussions also. And particularly Dr. Tapas Ganguly, KK Pons, Dr. Anandamurthy, Dr. Sendil Raja, Dr. Ram Prakash, who have really helped in getting the transparencies dressed. And then Dean Academic Dr. Sataram Mishra, Dr. C.P. Paul, Student Affairs, Dean Student Affairs, and all the major biomedical applications divisions. And last but not the least, Dr. S.B. Nakhe, Director RRCAT, who has guided all through. So that's all. Thank you. Any questions? I will take it.
I think we have time for just one or two questions. Yeah, regarding the RRCAT engagement with LIGO, I mean, what I was asking you yesterday, very broadly, I mean, without going into specific details, how much has been achieved, and what is the short-term goal and long-term goal?
I think Professor Shashank Chaturvedi can answer better in this way.
There's an echo, I can't hear very well. You're talking about the LIGO project itself, or in LIGO India? Well, what we've had so far is only a technology development and capacity building, a small project, just as a sort of lead up to the main project. We are still awaiting approval of the main project. In the meantime, at the site, the land acquisition and all that part is complete. Infrastructure building has started, building the lab spaces and so on at the site, and something for a guest house. So the infrastructure part is going off well, but we are waiting for approval for the main project. Okay. Yeah, please.
You told that beta-watt laser-driven X-ray source. Beta-watt laser-driven X-ray source. So how does it stand with respect to your synchrotron source, brightness-wise, or laser this metal jet source?
No, with the help of this, what I have told is that the petawatt laser has recently been installed, and with the help of this petawatt laser, you can have this kind of tabletop accelerator. So it is not yet done, so you can do it.
Okay, thank you.
Yeah.
Yeah, I have one question. That Raman spectroscopy technique that you talked about for probing beneath the surface, when you
Yes.
talked of tissue and so on.
Yeah.
What kind of depth can you go through and still probe at below that?
What is that?
What kind of depth? I'll give you an example. Suppose this table, suppose I have a metal table covered with plastic. Can it probe beneath the plastic and determine
It should be basically the light should be able to penetrate. That's the only thing. Metal shield, etc. you cannot do. But few millimeters to 1 centimeter you can easily probe.
of plastic and so on?
Plastic, etc. Plastic or papers.
And at what distance can this work? How far away can you be from
That is what the probing depth. That is around 1 centimeter you can probe.
No, that's the depth inside. How far away can the laser source be from the object?
So that you have a handheld probe.
Okay.
You have a handheld probe, so you just touch it.
Oh, you have to
on the
touch it.
surface, Yeah.
Thanks. Okay, let's thank the speaker again for a wonderful talk. Okay, the next speaker is Dr. Divakar from IGCAR. He'll be speaking about engineering activities at the IGCAR. Dr. Divakar will be speaking about engineering activities at the IGCAR. Dr. Divakar, please.
A very good morning to all. I'm especially thankful to Dr. Vasudeva Rao and Dr. Maity to make this in-person presentation possible. So I will be speaking about the engineering sciences at IGCAR. You have heard my colleagues, sorry, is that echo? You have heard my colleagues, Dr. Sivaraman and Dr. Chandrasekhar, speak about the physical and chemical sciences at IGCAR. This is only to describe, I will not talk about this. We are focused on establishment of sodium-cooled fast reactor technology in the country. And we have 2 reactors on site which are useful as facilities for our work. So broadly on the right, you see the groups that are there. We have heard of materials chemistry and metal fuels cycle group activities, as well as the MSc material science group activities, which cover broadly the chemistry and physics. I'll be talking today mainly about, if you see the view graph, the pie chart on the left, you would see this is the kind of thesis, about 102 in number, of which the bulk is from metallurgy and materials group, and the next highest is from RDTC, the reactor design and technology group, followed by electronics and instrumentation, and then the reprocessing facility. SQRMG, the safety and quality assurance, has been covered along with MSc last year. There are a few projects in material science group as well, which have a engineering focus. So broadly, I'll start with MMG. MMG is broadly 5 activities I can list, and these are physical metallurgy, where essentially we are focused on characterization of new alloys, and this is where we start with sort of alloy compositions that could be useful, and look at its thermophysical properties, look at its microstructure, property correlations, and things like that. And followed by the materials development and related technologies. This includes the materials development activity, where the focus is on indigenous production of these alloys in tonnage quantities for the reactors. That is the focus that we coordinate with industries like Midhani and the nuclear fuel complex to bring out new alloys into use. And we also are focused on the fabrication technology, including joining as well as the metal forming. And we look at also mechanical properties in static and dynamic modes. Corrosion science and technology is for the fundamental understanding of corrosion. Some part of it was explained by Dr. Shivaraman. Similar work is going on under engineering sciences, though the focus may be slightly different. Then we have the post-irradiation examination, which has come in as a co-located facility with the FBTR, the fast breeder test reactor, which was the first of its kind with carbide fuel. And we have contributed there with good assessment of fuels and other materials, all the other components. We have done a post-irradiation analysis, and this is the focus of the work. There is some research component that is over the last decade that we have brought in here. And last but not the least, the non-destructive evaluation is a highly matured division in terms of the work that is carried out there, which includes sensor development, it includes technique development, and it includes support to various surveillance as well as quality assurance functions in special cases. The normal ones are done by the quality assurance division where the techniques are established, but where we have a particular, I'll bring out some examples in that. So these facilities you have already seen in the physics presentation, the physical metallurgy. Largely, I would say our expertise is in advanced electron microscopy, and we have one of the latest state-of-the-art probe-corrected, what is called the aberration-corrected microscope here. And apart from that, we have a new EPMA, which is useful for diffusion and other studies. And we do have a range of thermophysical property measurement instruments, as well as a few synthesis-related instruments. And what we are looking at, one example of this, probably you might have noticed this in our physics slide, but I'll just say a little more about this, that this is enriched boron, which was indigenously manufactured and had to be qualified for use in the towards the 40 megawatt operation of the FBTR, and some part of it was done in the physical metallurgy. We have given the reactor designers the detailed assessment of the thermophysical properties as well as some microstructural information. I would just point out that at the bottom I have put in the faculty, which may be useful for contact. As contact for many of these, most of these slides I have included. If I missed one or two, I think you can always contact me, and I would be able to put you in touch with the correct people. The other one, we have seen this in Professor Paul's lecture yesterday from RRCAT, where they have these bushes, Deloro 50 alloy bushes have been made by them, and we have in physical metallurgy taken up a detailed characterization of these and looked at what is different in such additionally manufactured components vis-a-vis traditionally manufactured, what was earlier manufactured through a weld route. So these kind of studies are useful to optimize the process and also develop new components. Just to give a flavor of the high-res work, this is one thesis that we had in vanadium alloys, where on the left we have looked at nano-sized domains of omega phase transformation. And as I said, new alloys are brought in, first studied in physical metallurgy, and this is the start that we made at that time in on vanadium alloys, which are having some potential for use in reactors. And on the right, you see that we also collaborate with the mechanical metallurgy and try to understand those results through a detailed microscopy. This example is on nitrogen-added steels, nitrogen-added 316Ln variety steels, where we have looked at in detail at precipitates that come out at various things. On the left or top left explains our expertise in high-res analytical TEM, that in addition to the spatial resolution, we have added a chemistry component to that, and we are able to identify the atomic columns as it were. This is in transmission mode, so it's a projection. And so we are looking at atomic columns, and we are able to identify these in this. This is useful in a variety of ways, especially to find out such very small sized, sub-nanometer sized interfacial phases. And these have been developed here, and there has been several of the theses focused on oxide dispersion phases, and we have a variety of ball milling facilities for that under inert atmosphere, etc. And also we work on a number of other examples that I have not included for just to be to fit within the time. For example, the high entropy alloys and other phases also we are looking at. in detail. The corrosion facilities briefly was shown in the chemical sciences presentation. I would bring your attention to the bottom right of this, where we have engineering scale facilities where we can sort of design or research into what kind of cleaning modes or corrosion protection modes that we can advise for working plants, operational plants, and new facilities. So this is a sort of experimental facility where we can expose to different environments and different pH levels, etc. The other engineering level facility that we have is with respect to coatings. We have this high temperature chemical vapor deposition facility, which is being used to create these pyrolytic graphite coated crucibles. These are of use for the molten salt pyrolysis and molten salt, also the metal fuel melting applications. So there are a number of studies that have come out on this, including what kind of layers, what are the process parameters for coating, and what kind of interlayers help to improve the life of these coatings. We are looking at multiple meltings, how many times the crucible can be used, etc. And also we always look for improved coatings which give better this one. Further on, the top left shows we can have coatings of various metallics systems, ceramics, etc. And we also, this center panel in the bottom is what we do for steam oxidation studies. This is called steam oxidation studies. There's an example, I think, on the next slide on the bottom left. Essentially, when we have a development program for high temperature alloys where it is of interest to see the oxidation process in steam and air and other environments. And this is one example where we have looked at the phases that comprise the oxidation state and this oxidized layer. And this tells us a lot about what kind of performance we'll have in practice and where in type of corrosion, etc. there. I'm a bit rushing through because I have a number of fields to cover. But please feel free to ask for details. If I can provide, otherwise my colleagues will do that. So these are various coatings that we have looked at for, again, for the same thing. And this is one example of a recent thesis that has been accepted. And this is on, again, the nitrogen added 316 LN steels, where we have an interest. And this has looked at environmentally assisted cracking and how the crack initiation, what locations it takes place, etc. So the other focus has been on concrete, development of concrete. There are a couple of theses that are one ongoing and one, in this case, this is what is presented here is a completed one, where we have looked at fly ash and other additions to the standard concrete mixtures. And these have potential for improved corrosion resistance, improved durability, better densification and lower slumping, etc. These are things that are of interest for civil engineers particularly, and we have one collaboration with IIT Madras also on this. Coming to non-destructive evaluation, the non-destructive evaluation, as I said, is quite matured in terms of its understanding and the new developments that are taking place, broadly divided into 3 activities. One is just having those advanced ND test facilities, which are useful in a variety of ways for both the ongoing PFBR construction as well as many of the operating reactors, and also for some of the research projects that are there. And many of these, the central column shows the list of in-house developed facilities. These are, some of them are quite challenging, not available in India, and we have been able to make some headway in, especially the eddy current imaging and things like that. Further on, the facilities for ND-based materials characterization is listed here, and these are the kind of areas where the engineering sciences research scholars are there, and there are also opportunities for collaboration from other institutions. So briefly, the things are shown here, and as I said, we collaborate, I think, it was mentioned yesterday also from the BRC side that we are collaborating with them for analysis of NDE data, essentially. This NDE group is also serving as a third-party review for some of the data that is grabbed on various reactor systems, and also they go to various, they have examined various Calendaria and other systems in PSWRs where their work has been very significantly useful. So I'll just go to the bottom left. I would like to stress on that many of these sensors are built in-house, or rather made in-house. They are custom built depending on the application. And this capability gives us the facility to tailor these for even for challenging conditions, challenging environments, such as what we need to do in the hot cells for on irradiated materials. So we work closely, the two groups on PIE and this work closely to achieve this. This is an example which I will touch upon later when I come to the fabrication and high temperature alloy. High temperature alloy development. This is a actual component. It's a large component, about dissimilar weld, 400 mm radius, and I think the weld thickness is 250 mm. So it was fairly challenging. This process was developed at IGCAR by IGCAR people and has been implemented in BHEL. This is as a part of the advanced ultra supercritical alloy development, which we were a part along with NTPC as well as BHEL. So the ND part of this, this is a hollow section, a hollow component here, and then the ND was quite challenging to make over that 250 mm thickness. And this has been successfully demonstrated, and the technology has been transferred to BHEL. Looking forward, we are some of these, that is these two EMAT, especially the electromagnetic acoustic transducer, is something that we are looking forward to develop further, because this affords us several advantages, including high temperature operation, which we frequently want, and then also the couplant-free testing that is possible with this technique. So this is also the subject of a couple of research techniques. We are all familiar with eddy current done at a single frequency. We are looking at IGCAR at frequency sweeping frequency, so that you get a peak in the frequency image, and that corresponds to particular defects. That defect is now also being correlated to the state of the material, and we are looking particularly at this technique with irradiated materials, where I am sure in the coming years a few good engineering science research would come out. So I'll just skip this and go on to the thermography. Is a standard technique. It has been applied in our applied to find faults in electrical panels, and all these are the conventional applications. But on the bottom right, we are working on something called pulse-based thermography, which allows identification of fine faults in metallic materials. And in this technique, what we look at is the phase information rather than the intensity, and that makes it somewhat attractive for, as seen in this amplitude image, which is not so clear, and the phase image, which gives a lot more clarity in the surface defects. So we are also developing a tomography system. It is in-house developed, including the software for this. Of course, the components are bought out, and this has been the blue, yellow circles in blue that you see here are with respect to the sodium bonded metallic fuel pins. We have done some tests to find out the voids in the sodium, and this is something that we are studying and look forward to making more progress in this. So multiple techniques, ultrasonic, magnetic, synergetically used would help us get more data on the microstructure, and this is also the subject of a few engineering science projects that are ongoing at the moment. I'm rushing through this so we can have a detail on this in a more focused meeting on engineering sciences, or at some other forum, or we can have it over email, because I need to cover a few more fields. So as I said, we also support several other strategic sectors, including defense and space, with our NDE expertise. And this is a listing, a brief listing. Say dynamic NDE using acoustic emission and thermography is something that we are working on. All these are ongoing works, and we have completed couple of theses on one or more of these things, and we look forward to further working on that. This is amenable to collaboration also with interested. Now, coming to the materials development activity, first part I would like to talk about is the property characterization, mechanical property characterization, particularly with respect to fatigue and creep. These are of importance both for the fast reactor materials as well as all other high temperature materials. On the left, we have largely the fatigue testing. We have low cycle fatigue, high cycle fatigue, and thermomechanical fatigue and fretting fatigue. These things are set up, and the main unique feature that we have, the main unique facility that we have is in sodium testing of these properties. So this is a sodium loop in IGCAR to which these a special chamber has been developed where we can do the fatigue testing on these machines. And a similar setup is available for creep testing as well. We have the standard UniXL and other machines, the creep measurement, creep testing machines. But in addition, we have this in sodium, and we also have developed a biaxial creep instrument, which is essentially in-house developed. Metal forming and tribology is another activity that we have equipment for. I failed to mention that these are all high temperature capable instruments because usually our focus is on operation in sodium at 550, and so we do accelerated testing at as high as 700, 800, etc. And we have some of these torsion and compression machines which are required for arriving at process maps, as to say, that is at what temperature and what strain rate materials should be deformed, let's say at NFC to produce seamless tubes. So for new alloys, we are able to do a lot of experimentation and deformation process maps as well as the extrusion maps we can create here using these equipment. So broadly, these are the topics that are undergoing in the various studies, creep studies, fatigue studies, and then there is something called creep fatigue interaction, the interaction of the simultaneous action of both. These are the topics of several theses that are ongoing in the engineering sciences on various stainless steels as well as ferritic steels. And under metal forming and tribology, we are also looking at co-extrusion and things like that, which are useful for, say, mechanical clad metallic fuel or other things that might be useful. We were a part, as I said earlier, of the Advanced Ultra Supercritical project along with BHEL and NTPC, and these are some of the achievements there where we have developed at an industrial scale. That is, we coordinate with Midhani as well as NFC. Midhani for the alloy production and NFC for especially for the seamless tube production. And a variety of alloys have been developed and characterized, and then essentially we have generated enough data to for its use in components and for the further design of components by BHEL for NTPC. So two examples are given. One is with respect to fatigue crack growth, and other one is that rotor, which I said. This has been achieved by narrow gap TIG welding, and maximum 800 diameter welded rotor has been achieved with a weld thickness of 250 mm thickness. The welding group is quite advanced there, and it is very active, and it has a number of ongoing activities, including developing of welding consumables, some of which have been patented and transferred to industry. But much more development is going on, especially when we need to shift to, when we need to work more with nitrogen added, enhanced nitrogen 316L and steels and other materials. Then we are also looking at cold metal transfer for hard facing, and then we are where the dilution is issues is somewhat addressed, and we are looking to develop new techniques like a hybrid laser as well, laser welding, and also we have had one project with the ODS alloys that were developed. I did not mention that, but in physical metallurgy we have done a lot to, and of course across the metallurgy program. Done a lot to achieve cladding tubes of ODS, and that required a non-fusion welding, which we have done in collaboration, this magnetic pulse welding, which was done in collaboration with the BRC team, where some success has been achieved recently, has been shown. So the welding group as such has these on the development roadmap, the hot wire TIG and further work on the magnetic pulse welding and other techniques, dissimilar welds for various applications, and also the cold metal transfer and wire arc additive manufacturing, which will be very useful for some components. Coming to post-irradiation examination, the facility is co-located with the FBTR, as I said, and it is unique in the country as to being capable of handling alpha active, essentially alpha active material. And we have a team of dedicated PIE professionals who are experienced not only in carrying out the PIE but also in much of the equipment design. So until initially we were all about performance assessment, what has happened to the novel carbide fuel in the reactor, but then subsequently now we have brought in many more in research grade instruments such as the small specimen testing, electron microscopies, and other techniques with radial and axial gamma scanning, spectroscopy, essentially gamma spectroscopy, which allow us to carry out little. I'm giving only one slide examples in that, and in this, the first panel here, first row here is about small specimen testing, where the test methodologies are developed. They need to be understood with respect to the deformation mechanisms that are happening, the effect of various specimen preparation as well as the test equipment preparation details. These are worked out in for shear punch, and then we have also designed we have also qualified sort of in a subsize or ultra subsize tensile specimen where the gauge length is only 3 mm. The usefulness of this is as follows, that when we irradiate materials in the reactor, we should not, we prefer to have not too long a sample because of variations in temperature as well as the radiation dose. And because of that, there's an emphasis on these techniques, a number of these techniques. Bottom right is study done. We have a large repository of irradiated fuels. And we are now quantifying many of the effects on that. And this is one study that was done on the porosity in MOX and as well as carbide, mixed carbide fuels. And on the bottom left, we have one ongoing thesis on defect studies, defect characterization in neutron irradiated stainless steels, which we have recently concluded a second experiment at RRCAT synchrotron facility and brought the results. We are looking at it, and also the transmission electron microscopy of those to correlate to understand the formation of defects and the nature of those defects. And this is a general listing of recently completed thesis under metallurgy group. I'll move on to the electronics and instrumentation, where the mandate is on developing instrumentation and control systems for FR, essentially fast breeder reactors, and a wide range of things are there, including secure PLC, for example. And then there's a stress on wireless sensor networks, and then there are some various sensors that are required. Time domain electromagnetic sensor is one development that has happened there, and it is at the stage where it is probably ready for flight trials. This will be used for some exploratory mineral exploration in area in Andhra Pradesh. Sorry, Telangana probably. So then the IT related security is of high importance for systems like us, for institutes like us. And this is also being studied along with cryptography and other technologies that are required. So the facilities for under electronics and comprise a large number of standard ones and some that are unique to our place, in the sense that we have developed virtual reality facilities as well as a full scope replica operator. The virtual reality has been taken with great interest because this allows us to work with components that have been designed, that are just fresh off the design board without them even being fabricated. And this allows us to take it through its paces and then identify the faults and have a correction mechanism and all that. And then ultimately when it is finalized, it is also very useful for operator training. So these two are and also the other test facility that is unique, probably not unique, but important to us is the advanced calibration, the EMI interference, electromagnetic interference, and then the accelerated aging tests on many of these components, because we should also look at the reliability. In fact, reliability is a very big activity in this, which is going on. I have given two general interest problems that are being looked at. I'm not an expert. I don't have expertise in this, so I would not be, but I can put you in touch with, rather you can get in touch with Maity, who heads the activities. There is a good level of activity on smart sensors, so that's a 5-minute signal, sorry, yeah. Then I'll go ahead with this one. This is one activity which was going on in MSc, but it was being done by a instrumentation person. So I thought I'll mention it here. It was not, instead of including it in the physical sciences. Essentially what has been done is the EEG data has been collected on a number of patients. And then we have looked at how the cognitive memory load is reflected in these signals. And this will allow us to assess the operator attentiveness, app operator, also what is called the human-machine interface evaluation and things like that. So these are some of the electronics and instrumentation based projects that have been carried out in the group. Coming to reprocessing, two broad imperatives are there. One is equipment development. We don't get any equipment for free here, so or commercial basis. So much of these are developed in-house, and this is a big equipment. It is a cross-disciplinary science involving mechanical as well as chemical engineers, and a large number of such devices have been developed. Dr. K. Venkatesan heads the activities in reprocessing R&D. The other one aspect of it is process development, where certain modeling and simulation is also being carried out. And this gives, for example, when we want to assess a solvent extraction flow sheet for the plant, we can do simulations and find out how many stages, as the stages go on, what is the heavy metal concentration, how it varies and things like that. These are in-house codes are developed and they're compared with experiments. So both are possible in this group. The facilities include a variety of in-house built and some of them are bought out items here, but largely many of these facilities are built for the purpose that essentially of chemical engineering interest. Recent thesis topics in this has to do both with weld. You'll find some metallurgical aspects in this because huge number of tanks and which hold highly acidic liquids are involved, and so weld behavior under those conditions are of interest, as well as some thermal hydraulic investigations and other chemical aspects, chemical engineering aspects are examined there. The largest activity, but I'm spending less time on this because the area is very, very wide. Briefly, what the mandate of this reactor design and technology is the entire reactor. So we have now all the systems here, they have to be designed, they have to be analyzed with respect to thermal hydraulics, with respect to stress, with respect to seismic behavior. And there are facilities, large-scale facilities for testing all of these. So I have not listed them or included them in the slides for because it is too expensive. Maybe in a more focused meeting we can look at that. But we have facilities for testing in water, in sodium. We have a new sodium technology center coming up, which will be probably on stream in a couple of years or 1 year or more, which will allow us to do a number of experiments with sodium pumps, especially, and testing them and modifying the design as well as optimizing the design, optimizing the operational parameters of several of the systems. Most of the components that have gone into the reactor, we have a test facility called a fast reactor test group where these are tested. We also have a shake table that can 100-ton shake table that can subject components and various materials to seismic kind of loading forces, and under that we do a lot of reliability studies in this group. So a few of these are listed here. I could have come to this directly. Then I will also point out some of the sodium boiling characteristics in SFR and which are related to study. I'll just put on board three. Okay, before that, I'm coming to reactor shielding. Here, the main, as I said, Kamini and FPTI reactors are one of the equipment or resources, facilities that we have. Can I take just a minute? Yeah. So this is useful to assess. These facilities are useful to assess new shielding materials. So some of the experiments on the efficacy of tungsten carbide as a eggshell bottom shield in fuel sub-assemblies in FPTR, as well as for in-core shielding replacement of boron carbide with the ferroboron. These are all have been examined in this. And we have a high performance computational facility under which I'll just talk about two projects. I have three on slides, but I'll just talk about two. This is what happens when the core melts and then you have a core catcher. How do you design the core catcher so that the temperature under station blackout conditions can be maintained? So there is a study, there is a recent thesis on this. And we have come up with these heat pipes. They have come up with these heat pipes which can ensure that the temperatures are within control. So various configuration, multi-layer, and then various configurations of heat pipes have been examined in this. The other one that I would like to highlight is the pumps actually, and this is a simulation to assess the leakage paths in this. So these pumps, these kind of pumps have wear rings here, and they allow some certain leak path which have been simulated, and this allows us to improve the operational facility in that. So with this, I will close. There are a large number. This has been a difficult choice for me to choose this set. I really cannot say that because there are a large number of other works, which especially with respect to seismic shake table work and other things, which are also available at IGCAR. My acknowledgements, Dr. Venkatraman, to enable me to come here, and the faculty of HBNI from who have been running the HBNI show here along with me. Dr. Anish heads the Engineering Sciences as Dean Academic, and Dr. Trignanmurthy with Electronics, Ronald with Physics, and many others whom I have not included in all of this. Thank you.
Thank you, Dr. Divakar. Maybe time for just one question or so.
Professor Divakar, I was just curious, you mentioned this EEG study that is happening at IGCAR. What's the purpose of that EEG study? You mentioned this operators are being, analyzed for their EEGs. The EEGs, the electroencephalograms.
Okay. So that study, that's essentially what has been done is methodologies to process that signal to identify actions done by the human operator. So that essentially in this thesis, what has been done, a task has been given, a cognitive task, and correlated to that, what is the change in the EEG signal has been detected after removing standard interfering signals such as eye blink and a lot of breathing, and all those are also have signatures in the EEG, and it is required to filter out those to come up with something that has a high degree of correlation with the activity that is shown. So this allows us to both the final aim is that you can assess the operator fatigue kind of thing. If by design of different HMI, you can design HMI differently for different tasks, and it allows you to sort of optimize those and also identify the efficacy of your training methods. This is another goal that could be there. In fact, without EEG also there is a effort in, I should say, welding instrumentation, where by looking at the currents and voltages of that welding itself, there has been one thesis which has come out which has looked at that aspect, that how to assess a good welder from a bad welder. So these are some of the EEGs going on. I think some few, along with, they have collaborated with the Pondicherry medical team, I guess. Chandrasekhar would have been able to say that if he's online. And we are going ahead, we have sort of entered into MOU on this with them for further clinical kind of testing, more rigorous testing on this.
Okay, let's thank the speaker once again.
Thank you, sir.
The final speaker in this session is from NISER, Professor Brundaban Sahu. He'll be speaking about mathematical research at NISER. Dr. Sahu, please.
Okay, good morning to everyone. I am Brundaban Sahu from NISER Bhubaneswar. I am going to speak some of the mathematical research that we are undergoing in mathematics in NISER. So basically, I'll be proposing some of the basic questions that we are interested in. So before that, I'd like to thank Professor Rao, Professor Maity, Professor Naik for organizing this such a beautiful conference, in which it is kind of a good platform to show some of the glimpse of mathematics to other scientists in the institutes. Okay, so as you know, apart from our Institute of Mathematical Sciences and Harishchandra Research Institute, this is the third institute in DA in which we do this mathematical research. So we are a very young institute, started in 2007, and our PhD program started in 2010. So let me start with our program. So we have integrated master program. We have for this major as well as minor course. So they are the very basic core course in mathematics like real analysis, group theory, linear algebra, probability theory. We offer to most of the students and those who are interested in mathematics as well as some of the students in physics and chemistry. And we have also a set of very good elective course like percent differential equations, algebraic geometry, algebraic topology, manifold theory, Lie group, Lie algebra that leads to the students to go to the higher level and write a good thesis. And most of the students in the after masters, those who go for PhD program in abroad as well in India, this course really helped them to go do science in a better way. And also we have PhD program in mathematics. We have regular courses. We have kind of three basic mathematical courses: algebra, analysis, and topology, and complex analysis. And this regular course was make the students in a very nice foundations to do for the research in mathematics. Also, we are planning to start integrated master PhD program in mathematics. We have submitted the proposal to HBNI and we are waiting for the approval to start soon. And then we have the third program in mathematics. Okay, so let me tell something about research and outreach activity that we do in NISER. We regularly organize workshop lecture series on various topics of current research with the support of DAE and from the plan and non-plan both. And also we have a visitor program for research collaborations. We invite many senior and junior mathematicians to give short course or long course for research collaborations. Also, as part of our research and for short-term research for the students, we invite 30 to 40 students each summer through Indian Academy of Science and other Academy of Science Inspire, also through our NISER Summer Fellowship, to spend 2 months at NISER to work with faculty members for a project of their interest. Also, we have the outreach program that we started in 2016 following the program in Harishchandra Institute in Allahabad. So it's a 2-week program covering some of the basic topics in master level, mean for the students having very relaxed exposure. Basically, we invite students from the remote area. And then aim of the program is to give students exposure to mathematics through regular lectures, tutorial, interaction in evenings, and to motivate students to pursue in mathematics as a research career. So, as a facility and infrastructure, we have a very nice central library facility. We have a lot of mathematics books that we kind of procured last 10 years, and some of the e-books, and we have enough mathematics as well as computer science journal, and database like MathSciNet, Gesture, Project Euclid, Science Diet, all these things are available through GE consortiums, and some of the library expenditures from the central level facility. Also, we have departmental library. We have a small library with reading room facility, which is open for 24 hours, and which is managed by our MSc students. This is basically used for the senior, like the students who are writing thesis. They use this library very frequently, and they get benefit of this facility. And we have also enough facility in the computer laboratory. Okay, let me go to our faculty members. We have 20 young and dynamic faculty members. Now, the average age may be less than 40. We have 16 PhD students currently, and we have 11 postdoctoral fellows, and we have 60 master students. And we have the 13 PhD theses submitted to HBNI so far. And we're working, there are these areas like algebraic geometry, complex geometry. So my colleague, Dr. Krishanu, Dr. Ritvik, Dr. Sitabhra works in this area. We have analysis and probability group. There are various kind of analysis. For example, Dr. Khan, Dr. Kesari, Dr. Sutanu, Dr. Bikram, they work in broad area functional analysis. And Dr. Manna, Dr. Parvi, they work mostly on harmonic analysis. And Dr. Zana works in probability theory. So also we have a group of discrete mathematics and cryptography. Dr. Binod Sahu, he works in incidence geometry or geometry on the finite size and some of the graph theory. Dr. Patra works in algebraic graph theory. And we have a theoretical computer science faculty, Deepak Kumar Belai, that basically he joined NISER before the School of Computer Science came into existence in NISER. So he works in cryptography. Also, we have a recent member, Kosik Majumder. He joined and works in the area of combinatorics. Also, we have two members in NISER, Dr. Anupam and Dr. Manas. They work in partial differential equations. And in number 3, we have 4 members, including me, Jaban Meher, Dr. Santil, and we have in December, we have a new faculty, Sudhir Pujari, joined in number 3. So now I present some of the basic questions that we ask in mathematics. So the basic principle in mathematics to understand classify objects. So basically one question that one thing is same to other things. That's basically the motivations behind this basic questions. Let me start with, I'll put some mathematics in the picture. So we know that there are functions arise in very many situations, but we know polynomials, which are very nice functions, and there is theorem, there is a result in elementary analysis that every continuous functions can be approximated by polynomial functions, polynomials. So let's go further. Suppose we have differential function in real variables. So we fix R many points, and we fix some integers M1, M2, Mr, so that the summation of M1 plus Mr equal to D plus 1. Then there is a unique polynomial fx of degree D, such that the functions you take its derivative, j minus 1 derivative, that is going to match with the given functions of at all of these points for each point. So in other words, you get polynomial approximation of phi, but this polynomial approximation tell about the zero with multiplicity. As D increases, we get better approximation of these functions. So the same question can be asked in the multivariate case. Suppose you have a set of points, Ti, Si. This is in R2. And we have suppose integers, then what is the least integer D, so that there exists polynomial in 2 variables of degree D having Ti, Si as roots of multiplicity Mi for each points from 1 to R. So working over C, this problem has beautiful geometric interpretations, namely find the least degree curve in P2 of C that passes through the point Ti, Si1 with multiplicity Mi. So this classical problem was partially answered by Nagata in 1959 in his work with Hilbert 14 problem and gave a conjecture lower bound called Nagata conjecture. Okay, and basically Nagata conjecture says that suppose we have given more than 9 points with very general positions and integers M1, M2, Mr, and a curve we are looking for a curve, if a curve of inside P2 of degree D passes through these Pi's and multiplicity Mi, then D has to be bigger than this number 1 by root R plus this summation of this Mi that corresponds to the degree part. Okay, and the interesting thing, Nagata proved this for R is a perfect square, and rest of those cases are still open. So there is equivalent formulation of a Nagata conjecture coming from Seshadri constants. So basically the Seshadri constants tell about this 1 by root R, that's basically the Seshadri constant in this context. And the Seshadri constants were defined by Demeli in another professor C.S. Seshadri. And effective bounds of Seshadri constant can be applied to determine global generation of this line bundle, the geometric object. So our colleague Kishanu and his collaborator, they derive effective bounds of Seshadri constant for higher dimensional varieties. And I've given his email ID. He's interested in this kind of geometric questions. Now I'm coming to some of the works and some of the questions that we ask in analysis and probability group. So this group works basically on local smoothing of Fourier integral operator with applications to the wave equations and maximal operator. In particular, Fourier restriction problems for curves in RD in the D-dimensional real space. So Fourier restriction theory plays a key role in quantum mechanics. In fact, this theory is used to estimate the size of solution of Schrodinger equations in terms of the size of the initial datum. More precisely, we know how to define given functions, compactly supported functions from RD to R. we know how to define Fourier transforms. So for such a functions, the group is interested to study the behavior of f when restricted to a subset of Rd. For a subset S inside Rd, S can be any set. One can ask the following question: when this norm, they are the norm in the corresponding space, f at norm, and this norm of f in the corresponding LP norm in Rd, they are restricted and they are related by this particular relation for some of the constant related to the P and Q. So this has been a fundamental problem in analysis till 1970. And for S is a parabola or a sphere, a d-dimensional sphere, the problem has attracted a lot of attention by many mathematicians. And interesting result from Bourgeois and there are a lot of papers in these directions that the extreme measure means the one the equality holds in the previous equations. The restriction exists for all parabola in all dimension D and for all restriction pair P and Q. So this group interested similar questions. Okay, the paraboloid and the sphere are special kind of polynomial equations. So one can ask the similar questions for any general polynomial curve in Rd. And recently, my colleague Ramesh and his collaborator, they derived the existence of such extremal polynomial for monomial curve in Rd. The group also interested to study time frequency analysis and nonlinear disruptive equations and the interplay with the harmonic analysis. Let me come to one of the group. They're working on functional analysis. That's to motivate these questions. The notion of symmetry play important role in all branches of science. For example, the distance, pressure, transformation, or asymmetry in three-dimensional space are combinations of translation or rotations. And in the finite, very finite, as a set theory, the symmetries are nothing but permutation of elements in the finite sets. So in particular, the notion of asymmetry or Riemannian manifold has essential applications in mathematics as well as in physics. So the question is how to generalize this notion of asymmetry for non-commutative space like matrix algebra, non-commutative torus, and other non-commutative space. In these directions, Devashish Goswami from Indian Statistical Institute, Kolkata, derived theory of quantum asymmetry groups that generalize the notion of asymmetry group for compact Riemannian manifold. And this theory was applied to compute quantum asymmetry groups of certain non-commutative space appearing in the standard model of particle physics due to Chamsuddin and Cohen's in 2010. And we are asking the corresponding question: can we construct symmetry of M by extending these things in the homogeneous symmetry of M by this notion of translation quantum group? And Sutunu and his collaborator in these directions, they constructed graded version of quantum for the E2. E2 is our usual symmetry of the R2, but this is a non-commutative version of that. And we have a colleague, Dr. John, who works in probability theory. It's a branch of mathematics we study closely related to scientific experiments and phenomena. So he's interested in analyzing field models in theoretical condensed matter physics, and he and his collaborator use this the theory of large-scale deviations principle to analyze the phase transition in the midfield theory of statistical physics. He also interested in other branch of science like studying the theory of contagions, stochastic modeling of biological systems, as well as he want to apply these stochastic processes or random probability distributions in the field of economics. Coming back, we have another colleague, Dr. Dalai, who works in cryptography. So as you know, the cryptography is the practice and study of techniques for secure communications in the presence of third party called adversaries. So it is branch of mathematics as well as computer science. And this concept comes from number theory, algebra, discrete mathematics, probability, and statistics from mathematics, and theory of computations and complexity algorithm from the computer science. So he's interested in analysis and construction of cryptographically significant Boolean functions, and analysis and design of stream ciphers, and analysis and design of post-quantum lattice-based signature schemes. Recently, Deepak and his collaborator, they studied the cryptanalysis on NISER and Grain 128A, which are two recent popular stream ciphers in these directions. Now, coming back to the group of partial differential equation in NISER. So they works in conservation law in one space dimension as well as in the multi-dimension, and delta weight applicable for conservation law of the particular type that we call non-strictly hyperbolic. The main goal of this group is to show the existing solutions of some suitable function space, namely function space of bounded variations. They study uniqueness of the solutions by imposing physical proper conditions known as entropy conditions. They also study large time behavior of solutions and structure of the entropy and admissible solutions. Since these solutions are important equations coming from physics, only the existence may not useful practices like we do in mathematics, but this group also interested to study these numerical schemes of these systems, their convergence, analysis, and order of convergence. So some of the model, the work in progress, the large-scale structure of structure formation of universe, addition model, zero pressure gas dynamics equations, and general one-dimensional conservation law applicable for any model. Also, conservation law with the discontinuous flux. And recently, Manas and his collaborator, they found explicit formula for the solution of one-dimensional zero pressure gas dynamic systems for initial and boundary value problem. And according to this is the new for the boundary value problem at least. So Dr. Manas and Anupam, they work some of the equations that arise from physics, and they're interested in this kind of equation in PD. Now, let me come to our topic, the broad topic. I'll discuss some of the things we are interested in number theory. We are interested in modular forms and some of these arithmetic of Fourier coefficients. Also, we interested on the differential operator in modular forms, and some of the L functions and these zeros attached to modular forms. Also, we have a colleague who works in transcendental number theory and multiple zeta values. So let's, we know that the complex number which are roots of some polynomial, we call that over rational, we call the algebraic number, like √2 and the complex number I. But some of the numbers which are not algebraic, that we call the transcendental numbers. And we know that the algebraic numbers are countable, and these transcendental numbers are uncountable, but there is no definite way how to construct transcendental number, although there are more uncountable compared to the algebraic number. Now, this famous Hilbert 7th problem asks, is 2 to the power √2 is transcendental? So the answer is yes, and was proved by Gelfand and Snyder independently. Now we have this famous Euler identity, E of I pi, e to the I pi plus 1 equal to 0. And this motivates to study linear independence and algebraic independence related to the values of exponential functions. So to understand the algebraic nature of the numbers like pi, e plus pi, e to the pi, or pi to the e, we relate which are functions related to the exponential functions. One may need to understand the values of Weierstrass, elliptic, zeta, and sigma functions. So for example, in the Nestorenko's proof, which is important result in these directions, he proved the algebraic independence of pi and e with the inverse Weierstrass elliptic functions. And also this elliptic function is important to compute this elliptic integral. One of the several things of the transcendental number theory is to find transcendence degree of fields generated by the values of the classical exponential functions and the values of these elliptic, Weierstrass elliptic, zeta, and sigma functions over Q. One of the questions that we ask, when these fields have transcendence degree at least 2 over the field of rational numbers. And this requires the study of algebraic groups of commutative algebraic subgroups of commutative algebraic groups connected with these functions. Recently, my colleague Sendel proved this transcendent degree of the field generated by certain values of Weierstrass elliptic and zeta function at least 2 over Q. Now, let me tell something that we are interested in the modular forms. So let me write this set of integers, and given a number, we are interested in the sum of all divisors. And if there's something like R, we take all power of the divisors and we write sigma Rn. So if it's sigma 0n is just sum of divisors, number of divisors of n, sigma 1 and sum of divisors of n, we call it sigma n. And we're interested on this sum, namely convolution sums. We take the sigma R, L, sigma Sm, and now we take this L and M based over integers, and we take the AL plus BM equal to n. So why we're interested on this particular sum. So just wait for R equal to S equal to 1, you just denote by AB. We forget about the RS, just putting 1 on 1. And this kind of sums has been appearing in mathematics in early base J in 1862. Gleiser, Ramanujan were interested. Also, there D.B. Larry in 1947. Their works appear this kind, computing this kind of sums. Okay, one can ask why these kind of sums are important. So there are several recent work in 1990, and there are several methods, something like elementary evaluations, something like PK parameterization using modular forms, and all using quasi-modular forms. Okay, so interested to evaluate the sums, we are interested in one direction, namely these sums may be used to find the number representation of natural number by certain quadratic forms. Okay, I'm giving one example. So we have this Jacobi formula. There is a theorem of Legendre that you take any number, positive number n, you can always write as sum of 4 squares, but you cannot write as always sum of 3 square or 2 square. So in the directions, Jacobi proved this nice formula that number representation of a natural number as a sum of 4 squares, counted how many ways you can write. You can write as something like 8 sigma n minus 32 sigma n minus n by 4. Okay, whenever this n by 4 is not a natural number, we think this is 0, sigma takes 0 value. Okay, now we can ask the question, the number representation of a natural number as sum of 8 square. Okay, if you want to write the sum of 8 square, then you want this kind of convolution sum to come into the picture. This is one prototype example. Similarly, if you write this particular, instead of sum of squares, I take this number of the form something like x1 square, x1, x2 plus x2 square, x3 square, x3, x4 plus x4 square. How many ways we can write given a number in these forms, and there's a general interesting formula, something like 12 sigma n minus 36 sigma n by 3. So we can ask the question, what about the similar question in 8 variable or 12 variable or more variables? And in these things, we use a theory of modular forms and differential operator to give a general way to evaluate convolution sums. There are several articles in this convolution sum, but they use different method to have one convolution sum, but we use the modular form differential way to give one unified way to compute these modular forms. Okay, so what are modular forms? Modular forms are special functions like our usual trigonometric function sin x cos x, but like they are periodic functions. Also, they have something more. They have periodicity plus we have enough symmetry in that they're essentially unchanged on the large group of substitutions. So symmetry comes to the picture, the group of symmetry, and symmetry allows the modular forms to write as the Fourier series. We have this nice object summation a n qn, where the q equal to e to the power exponential 2z, and the coefficient an of modular forms contains a lot of information about various important aspects. Namely, it may contain the information number of representation of integer by positive definite binary forms. It may represent something called class number of quadratic fields, which measures basically how far this is not being a unique factorization domain. And some of the values of the combinatorial functions like partition functions or other kind of partition functions. Also, this contains information about geometric object, the number of points over finite field of certain algebraic varieties like elliptic cos, K3 surface, and Calabi of 3-4, etc. So looking at this importance, and there is a mathematician Martin Eichler, here is a nice quotation that there are 5 basic fundamental operations in mathematics: addition, subtractions, multiplication, division, and modular forms. So I already told what is a function basically from the complex upper half plane to C, and we have this group of, this is the simplest form of the modular form. This modular group SL2Z come into the picture. And SL2G act on this space of upper half plane, namely the Mobius transformation, Z goes to AZ plus B by CZ plus D. And we're looking for functions which are invariants under these actions. Okay, here there is a there's a weight K come to the picture. One can take K to be 0. In that case, you want something like this completely invariant, but there are not many interesting functions if you take K equal to 0. So we take any general K. And it has a nice Fourier expansions. Okay, so this space can be like adding numbers. This the functions can be added, and they have the structure of vector space structures. And I've given one of the example that appears in called Eisenstein series. Basically, you take a lattice and you take sum over this mz plus n to the power k. You take the reciprocal and sum it over that. They are the nice functions that follow has these kind of functions. And more importantly, the Fourier coefficients, that's what I've written here, 3, E4, E6, E2, there the sigma 3, sigma 5 appears as a coefficients. Okay, so now we come to these forms. So we can multiply 2 forms. And in these directions, we have a nice Ramanujan functions. Basically, we have this, take this product series q to the product 1 minus q to the n 24, and the coefficients are called Ramanujan tau functions. And these Ramanujan transforms are very interesting functions. And in his 60, Ramanujan he made some conjectures after studying this value, namely tau is multiplicative, and tau at the prime p power takes this kind of rules. They follow this kind of rules. And more importantly, this bounds of tau and the upper bound of tau n is less than equal to this n to the 11 into by 2. This conjecture by Ramanujan, and it was proved by Model in 1921. And there is a new theory called Hecke operator developed after these first two conjectures. And the last was proved by Pierre Deligne in 1974 as a special case of well conjectures. And he awarded Fields Medal for this proof of the third conjectures. Now, there is another still conjecture called a Lambert conjecture in these directions. This says that tau n is never 0. And so far known that this tau n not equal to 0 up to something like 8 to the power 10 to the power 24, but it's still a conjecture. And it is interesting to study this tau n congruences. Okay, now there is a differential operator. So why is differential operator interesting? So we can use this differential operator to create new forms. And basically the differential operator kills the symmetry, but we can bring back the symmetry into the picture with suitable combination of these different forms. And there are something called Rankin-Cohen bracket. In that particular thing, given two forms, we can have possible combination of all these things with the finite sums that can be brought together to create new forms. And there are several identity one can use using the difference operator. In particular, these two identity proof in 2011 some occasion connecting this tau and this sigma kind of functions. Now there is another operator called Ramanujan shared derivative. So basically we use this E2, which is not a modular form, but it's quasi-modular forms. And these equations are among these modular forms. These three are proved by Ramanujan. And one can generalize this operator. Basically, there is operator coming from the modular forms. Basically, you use a operator with k, and you take this twisted with E2 to get a modular form with k plus 2. So basically, this operator gives you new forms. Okay, and there are nice arithmetic application of these forms. So, using this differential operator, recently we proved that one can give a general way of computing these evaluations of these convolution sums. Those are the use of this one. Okay, so let me sketch this slide. We have another way of computing use of modular forms, namely all the sum of square, etc. There are particular case, sum of 4 square or sum of 8 square. But what can we ask for general quadratic forms? So we use, there is limitations with this convolution sum. So we use some method of theta series, and we create this. Basically, we associate a modular form called the theta series, and using this now online database of modular forms, and we have this search method like the open software, you can explicitly compute this representation of natural number by quadratic form. And some of the prototypes are these kind of forms. And as you know, these modular forms are generalized to Ziegel modular forms and Jacobi forms, which is immense use in physics or theoretical physics. And some of the publication I like to show in these directions, we are interested in this differential operator and some of these zeros of the functions with my colleague. Now, some of the workshop we plan, in number 2 interesting workshop, I like to mention one workshop in this platform. We organize a school and workshop on modular form and black holes in 2017, in which we bring theoretical physics and number theories together, and there are intense lecture series in these directions. Okay, I would like to thank all of you for your kind attention. I like to HBNI for this platform to this. Also, I like to thank Director NISER for his kind encouragement and all the faculty members who have provided me with data of their works. Thank you very much.
Thank you, Dr. Sahu. We have time for 1 or 2 questions. Okay. Okay, no online questions either. Okay, so let's thank the presenter again. That we come to the end of the session. Thank you.
Thank you, sir. And I thank all the speakers for finishing on time. We will now break for about 15 minutes and So welcome back to the final session. For chairing this session, I humbly invite Professor V. Ravindran, the Director of Institute of Mathematical Sciences, Chennai.
Good morning. Welcome to the last session of this wonderful meeting. Before I begin the last session, on behalf of members of our Institute Math Science and also all the members of CIs and OCCs, to thank Professor Vasudeva Rao, Vice-Chancellor of HBNI, and Professor Nayak, Dean of HBNI, and Professor Maity, Associate Dean of HBNI, and his wonderful team, active team, who actually made this meeting extremely successful. And also for, want to thank for, conceiving this beautiful idea of bringing all of us to this meeting, and also allow us to talk about what we are doing in our institutes, and showcase our works to all the other members of the HBNI, and also had an opportunity actually to listen to what other CIs, members of CIs are doing under the HBNI umbrella. So it was a unique opportunity, I must say, that we could hear, also we could actually sort of tell everybody. I think, having said that, I must say that it's just a beginning, because this is a unique meeting where we spoke about our academic activities here, not just the administrative activities of HBNI. And in that sense, I think, all of us benefited quite a lot. And also, there was talks from abstract mathematics, algorithms to, life sciences, the kind that, we cannot even imagine, curing dreaded disease like cancer. Amazing things that are being done in our organization. And I think it is a wonderful meeting. I want to thank on behalf of all of us actually. And let's thank, our VC and Deans for this nice, meeting. And having said that, actually, we should not stop here. This is just the beginning, and we should continue this actually. We should time to time have meetings of this kind, dedicated to discussions of this kind, on regular basis, and take a stock of everything at the end of the year, and continue to do that. Actually, I think that would be the way forward, so that the initiative by our Vice-Chancellor and the Deans to actually make it successful in the years to come. So with that, actually, I begin the session. We have two talks, one by Subhasish and the other one by Sitabhra. So I call upon Subhasish Chattopadhyay to talk about the activities of the VECC. Thanks.
No, it's okay. Yeah, okay. Good morning, everybody. I'm going to present here the activities at VECC on basic science. Now, my colleague, Dr. Arup Bandyopadhyay, he has given a presentation on 6th about the general facilities and the engineering aspect which are available at VECC. So this presentation is basically a complementary to that presentation. So before I go into the main subject, I would like to show, because this is an HBNI event, so I would like to show a glimpse of the vibrant HBNI activities which are ongoing at VECC. We already have
more than 80 actually, students who have got their PhDs and working in different places, including permanent positions and postdocs. And presently we have 50 students who are enrolled in PhD. And out of that, 18 are kind of employees, namely training school officers and technicians. 32 are different kind of fellowship as a student. And this is the breakup maximum. Most of them are from nuclear physics, working on nuclear physics. So whatever I will be presenting here, essentially in all of them, 1 or 2 students or more students are involved. So in that sense, whatever I will be presenting is basically for HBNI students and faculties together. Now, I don't know how many of you, I hope everybody have visited VECC campus, which of course we have 3 campuses, but then the one which is the main one called Bidhannagar campus. Now, I would like to show you a collage of some of the figures, some of the pictures, which will take you a little bit a decade or 2 decades earlier. And this is the picture which is around 1960s or 70s, when some of the personalities of that time, with the dream of having a cyclotron in this field where there was power cut was the order of the day, were crossing the bridge with an umbrella to face the rain and the storm of Calcutta at that time. And this was followed slowly by the indigenous development of the machine. One of the main component which is shown here is the D of the accelerator, which is connected to the RF for the RF power generation under the watchful eye of Professor Dr. Rajaramanna. And then this is today, which is a drone picture, where you can see our campus, which is the Bidhannagar campus, which is full. And all the bridges might have been kind of now full, and it's not enough to do anything more now. So we have extended our facility, our campuses. We have now 2 more campuses. One is in the eastern fringe, which is in Rajarhat, Newtown, Calcutta. And another one is the southern end, which is called Chattopadhyay campus, where our medical cyclotron facilities are situated, which was discussed on 6th by Arup. And of course, there are many eminent visitors in between. And one of the figure is showing Professor Abdul Salam, with Dr. Vikas, our former director, and Dr. Bhandari, also our former director, listening to him. Now, I have tried to put my talk together thematically and schematically in one slide, which essentially says what we do at VECC, so far as the physics research is concerned. Now, this is the time after the Big Bang, and it goes today after 13.7 billion years after the Big Bang. Now look at about a microsecond old universe, which you could look at these pictures again. This is essentially the similar picture, but more colorful. But the point which I would like to draw attention to is a microsecond old universe where there is a statement which is said, I don't know if it can be readable, is called nucleons form. So if I draw an imaginary line here, on the left there are symbols like Q, G, E, and on the right there is no Q, there is no G. That means these quarks and gluons, which were free before the microsecond old, they got caged or confined inside what is called strongly interacting object called hadrons, like protons and neutrons. So what has happened in our field of research, what we try to do is to recreate that universe, microsecond universe, create something which is called a soup of quarks and gluons, or the deconfined states of quark and gluons, and study them. First, we see that if we can make them, create them, and then study their characteristic, which is the one which is 10 microsecond. Subsequently, of course, nucleons like protons and neutrons are formed, which are followed by the formation of nuclei. And this is what is the core activity at VECC. Now, there is one theme which is common for all of them, that we use beams or particles from particle accelerators to create these kind of situations and study their properties. And so we have extensive studies on the nuclear physics, producing or synthesizing different kinds of nuclei, study their properties and how they are formed in the reactions. Of course, this has been followed by atoms, molecules, and materials, where we confine ourselves in studying the properties of the materials under the irradiation. Now let's make a zoom of the nuclear physics part of it. If I have on the y-axis number of protons, which is Z, and the x-axis number of neutrons, which is N, then all these black lines is essentially at 45 degrees. So that means N equal to Z. And these are the stable nuclei. Most of the stable nuclei are around where N equal to Z. If you go towards this side, which essentially takes you towards the higher number of neutrons, it will start giving you a beta decay and it will remain unstable. If you go towards the higher number of protons, it will be coulombically dissociated and it will be unstable. So on the stable part is in between, but then as the quest goes, we try to synthesize them, which are neutron rich or proton rich, and whatever duration they remain before decaying, study their properties. And this is what is the aim, synthesizing these nuclei of different types, which may be spherical of different shapes, and then study them. There are, of course, something which can be done in VECC, which the cyclotron, which Aruk has discussed, and there are something which is called heavy elements, which is beyond, let's say, 185 and others, or He, followed by C, or super heavy elements, which could be created, which are being created by laboratories abroad like Dubna or GSI in Germany, where our researchers from VECC take part and to study them. This is another extreme. We study nuclear physics. We study nuclear matter. We study nuclear matter under excited state. We study nuclear matter under ground state. We study nuclear matter under extreme conditions. What are the extreme conditions which are depicted here? One is under extreme temperature. Another is under extreme density. What do you mean by extreme temperature? How do you create them? You collide two lead ions, which is having 208 protons and neutrons put together and collide with such a high energy, like available in Large Hadron Collider at CERN, where those protons and neutrons which are baryons, they're swept away. And in the middle, you have only energy. And from those energies, you create particles like pions and others, E equal to mc square. And the number of particles which are created because of this huge amount of energy is such that the quarks and gluons which are inside these protons, they become indistinguishable, and you create something called quark-gluon soup or quark-gluon plasma. This is the deconfined state of quarks and gluons. You can reach at the same goal if you just compress it, namely that you have one proton and you pump up in this volume 5 protons. So the density becomes 5 times higher, and that time also the situation will be similar to that. And they have a comparison with two astrophysical objects. One is, of course, the early universe, which you talked about, which is the microsecond old universe, which is a hot quark-gluon plasma, the state where quarks and gluons are confined. Not confined, they're deconfined, and then they got confined inside protons or inside the core of the neutron star, where there are only neutrons. And the density, like somebody says that you can, some fingertip of neutron star weighs like Eiffel Tower. So neutron star is such a heavy object and such a dense object. The core of it doesn't have neutrons and protons, but has only quarks and gluons, which is in the form. And we create them, study them, characterize them in the laboratory. Now, before going into the actual activities, so far as the experimental part is concerned, we have a very strong theory group. And these theory groups are essentially help us, like us, an experimentalist, both low energy physics experiment and the high energy physics and high energy nuclear physics experiments, to give new theories, to give new directions how we should go. I will give a glimpse of it. This is the slide for the low energy physics experiment, which is not the whole, of course, is only a part of it. On the left, I saw the effect of the nuclear physics when you increase the density, neutron density. What will happen to the binding energy? It has been shown that the binding energy gets modified if you have more number of neutrons. This has been shown and published. And this is the one which is even more interesting for a neutron star at the core of neutron star. Neutron star has been found to have a mass which is 2 times the solar mass. A neutron star held by gravity and 2 times the solar mass is a huge object. And you have to understand what is the equation of state inside that. Otherwise, it will just collapse or it will just scatter. And what has been done is this equation of state. This assumes that this is made of quarks and gluons soup, that means quark-gluon plasma. And then quark-gluon plasma is essentially confined in a bag and under a pressure, and that pressure is given by something called bag constant. If the bag constant is variable, then you can reach to 2 times the solar mass. If it is a constant and the value which is accepted may not reach here. So this is the result for neutron star. And there have been calculations done, which I call is a hybrid model, which is a nuclear energy density functional and statistical model. They could explain the fission yield, the mass distribution and charge distribution very well. And this is assumed that before the season, these nucleons get rearranged, and this calculation can be done very fast, and it is done with thermal neutron, with uranium, which is having a potential applications in DE program. Now I go to the high energy nuclear physics, where two heavy ions collide, like lead on lead or gold on gold, and create something which we assume to be a quark-gluon plasma. But who told you that that is a quark-gluon plasma? You may not have a deconfined phase because you do not know. It happens in 10 to the power minus 20 seconds. Your detectors respond in 10 to the power minus 9 seconds. So what happens in between? So the theory says that there are some smoking gun signals, which is the job of the theoreticians. Look for those signals. If you find them, then at least I will agree, yes, something like that has happened. And those signals, because this collision point that happens and it gets evolved. While it evolves, it produces different kind of signals. One of them is the photons. It's like radiation. So it's radiation. If quark-gluon plasma is formed, it will have a different kind of spectra or different kind of collectivity or asymmetry of the whole zone. Or if it is not quark-gluon plasma, it will be different. So this is what is shown here as the theoretical understanding. And then this is production of strangeness. Protons and neutrons doesn't have strange quark. Strange quarks are produced when they collide, when you have enough energy and the phase space is occupied with the U and D quarks, and then strange quarks are produced, which is likely to be more produced in quark-gluon plasma, and this has been studied and then matched. A model has been built which will study the evolution of such a system, and this is being used for making the prediction. Now, this is my last slide. So far as the theory part is concerned, this is very interesting. Higgs boson explains the mass of the elementary particle. Which particle? Electron, quark, and all others. Now, you know, look at this figure. There are different kinds of quarks. U quarks, D quarks, strange quarks, U quarks, D quarks, strange quarks, charm quark, bottom quark, top quark. And the green part is explained by Higgs mechanism. So far as the charm, top, bottom and top are concerned, are completely explained by Higgs mechanism, whatever mass we know about. Strange is mostly, some part is missing. And look at U and D quark, of which U and I are made of. Only 5% are explained by Higgs mechanism. The dynamic mass of U is 5. If you put in a proton, that will take you 15 MeV, but proton mass we all know is 1 GeV. Where from does the other one comes? And that is what is the chiral breaking, chiral symmetry breaking, and that is what is because of the gluons. It's a dressed up. So what is assumed is, or what is said, that in heavy ion collisions, these dressing will go away, and this U and Do will get their dynamic mass, bare mass, and that is what is the chiral symmetry restoration. Now my colleagues have done that in these heavy ion collisions, there will be huge magnetic field, because these lead ions are basically moving ions that will create a magnetic field. Under this magnetic field, what will happen to the chiral partner, like pi sigma or rho and A1, which he has shown that the spectral function will essentially look similar with or without the magnetic field. Now I come to the research facilities at VECC. Arup has already talked about 3 cyclotrons. One is room temperature cyclotron, which is our workhorse, which is a K equal to 130, which is giving proton beam, alpha beam, and heavy ion beams of this type. In addition to that, we have accelerated deuteron, we have accelerated sulfur, we have accelerated argon, and more beams could be produced. We have the technology for that. And this is the one which is the next generation one, which is a K equal to 500 cyclotron, which is having superconducting magnets in the middle. And this cyclotron also has accelerated already nitrogen beam and neon beam and extracted them. And as I heard yesterday, they have also extracted oxygen beam. So we are essentially now opening up a new era at VECC from this 130K to 500K, where with higher energy, you will have a new region of nuclear physics research which will be opened up. And then medical cyclotron facility, which is a proton machine of 15 to 30 MeV, that is being essentially used for radioisotope and radiopharmaceutical productions. But then there is a beamline which will be studied for material irradiation as well. We have another facility which is coming up, which is production of rare ion beam, which Arup discussed in detail yesterday. There is a beam line from room temperature cyclotron which goes through the helium jet to a facility called radioactive ion beam. And these are the radioactive ion beams which are produced already. And these are the half-lives starting from 71 second to 20.4. And these are the channels that has been used. And some experiments are already being done. But most of the efforts are on the material science study. Now, I would like to take you to a different type of activities at VECC where we pay most of our attention to, which is the development of detectors, electronics, data acquisition system, and computer system. Because unless we have them, there is no point of having accelerators. And I just for fun, this is I sometimes do, I was looking at a history of the Nobel Prizes starting from 1901, which started with Röntgen with the discovery of X-rays, to 2013, which is the latest one by Peter Higgs and Engg, who got Nobel Prize for Higgs boson. And look at it in between. 1903, electrometer by radioactivity, 1908, atomic nucleus, 1927, cloud chamber, 1935, neutron discovery, pion discovery, antiproton discovery, CP violation, WN jet boson, muon neutrino, and all others. These are the major discoveries which have essentially shaped our field. But then I would like to draw your attention to the last column, not the first three. Of course, first three are most important. What is the last column? The first one is X-rays discovered because there are photographic plates there. Radioactivity was discovered because there are electrometer. Atomic nucleus was discovered because there are scintillating counters. Neutron were discovered because they are in ionization chamber. Pions were discovered because they are a photographic plate. This antiproton was discovered because there are Cherenkov counters, and like that. So that means for each and every discovery that follows has to have a device which will be sensitive enough and having proper parameters which will be able to catch it. And this is what, in my opinion, at least in VECC, the both high energy and nuclear, low energy nuclear physicists, experimental nuclear physicists spend a lot of time in building detectors. And we love to do that. And then, of course, we get the physics and love to have the results after that. So this is what is the journey that I will go quickly. So these are the three beam lines which we have. And now you see this happened in 1977 when we first got our beam. And that time we only had a scattering chamber, of course, and inside the scattering chamber there are silicon detectors of this size and silly detectors and gas ionization chambers all made at VECC. And when I joined VECC after training school in 1988, this was the scattering chamber where I did my first experiment using these detectors. And then now look at today. Today, of course, silicon has been replaced by silicon strip detector, cesium iodide, thallium, multi-layer proportional chamber, and all others. But the emphasis is not to have small isolated detectors and take data. Emphasis is to make a detector system which will have try to have a 4-pi coverage, and all the particles which come out, neutron, charged particles, photons, measure their energy as precisely as possible, measure their time as precisely as possible, and identify them. And then only you can do complete physics out of it. So I am going to one facility after another. First one is the charged particle detector array on kinematic reconstruction, which is called Chakra, and which is having forward and backward detector. These are the charged particle detector with delta E type. That means delta E is the detector, maybe gas detector, which will deposit some energy. E is the rest of the energy. And if you look at E delta E plot, then it has identification power from one element to another. And there is a forward part which is having higher energy. So these are the special detectors and these are the backward parts. And these are the detectors which are built with 3 different types and operational at VECC. This is large area gamma detectors, which is called lambda. And this consists of barium fluoride array, which is there are 3 main arrays which you can kind of modular, so which you can change the locations and have good coverage. And these are the ones similar detectors, but larger in size, because this will only tell you how many photons have happened, and these will measure the energy, and these are small in size and these are larger in size. So this is another facility. Then comes the neutron detector. So I have talked about charged particle, I have talked about photons or gammas. Now I am talking about neutron detector. These are in our superconducting cyclotron facility. Now, in these neutron detectors, we have done research on liquid scintillators and the time-of-flight detectors. The one which are shown here is surrounded by a scattering chamber where the target will be sitting and the neutrons will be produced along with the charged particles. It will be measured inside the scattering chamber. Though the scattering chamber is very thin, so the neutrons do not get stopped. It comes out and will be detected by these detectors which are shown here. Now, one of the special feature of this thing there, so you can rearrange your structure there, and this is what is neutron array. Now comes about photons again, or gamma again. There are two arrays. One is called Venus, VECC array for nuclear reactions. Another one is Venture, which is essentially photon only, using the specialized high purity germanium detector for added to a cesium bromide detector for time measurement. So when you have energy and time, then you have a better handle to understand the reaction or the structure of that you want to study. And this is the final one which I want to discuss here. There are many more, which is the penning trap. Yesterday we heard about quantum computing, and one of the options is to use penning trap as a device which will be used for qubit. Now, penning trap activities is going on in VECC for quite some time, and our aim is to have trap the ions inside superconducting magnets, but then we have achieved something only recently to trap electrons, not ions. This is a maybe long way to go. And this needs a lot of technologies which is inside the vacuum, inside the superconducting magnets. So this is work which is going on. Now, as you all know, detector is not enough, accelerator is not enough. You have to have data acquisition system because you have to collect the data and then analyze them. We in 1970s built our first data acquisition system based on the standard called CAMAC. But then there was a old computer called NORDS data, maybe some of you might have used it, 560 that was there, which is now dismantled, but the CAMAC still alive. We are still using that. And then now it has mostly been replaced by VME standard. Then comes the computer. VECC has a dedicated computer called Himalaya, which is a high purity computing clusters, which is having 2,256 total number of computing core and 500 terabyte of disk space, which is for general purpose computing for any research work which is going on at VECC. Now, at this point of time, in continuation to the computing, excuse me that I am shifting the gear to high energy, but then I have to talk about computing facility which is existing at VECC, which is called Tier 2 LHC grid computing facility. And VECC is a node where we have this computing. What is this Tier 2 grid computing facility? And if you look at an experiment in LHC, let's say CMS or ALICE or Atlas, and then the data which is collected by the detectors, you put in a CD, whatever highest volume CD you have, highest capacity CD you have, and make a stack of these CDs for 1 year of operation. And the stack will go when the airplane flies. And if somebody says, now analyze this and find Higgs boson from that or quark gluon plasma from that, with the computer that you have, it is not you, maybe it's the next 2 or 3 generations which will take to analyze to find something. But that did not happen. What actually happened, within 3 months of data taking, LHC could find or announce the results. How did it happen? Because all the computers which are there under the disposal of the collaborating institutes, put them together with high internet and give a job anywhere and see who is free and then get it computed. And this is what is called grid computing. It's like a power grid. So we are one of the nodes in India, which is running 24/7. We are having 4,000 core and 1.5 petabyte of storage and 16 gigabits of network. Now I'd like to show some of the results. These are not the full set. This is only a few which are published in high impact journals, but then also it draws attention in general. So I picked up some of them, but this is the glossary list. Each of the topic might have 7 or 8 publications. So this is a fragment emission mechanism, angular momentum dissipation, deformation studies, temperature measurement. These are all nuclear physics, nuclear matter and nucleus itself, cluster structure, formation of equilibrated system, which is not a compound nucleus, but a rotating dinuclear complex. Of course, fission studies, which is one of the basic studies. Collective nuclear excitation. We have to see whether the nucleus behaves like a liquid drop or something else. And then nuclear level density parameter measurement and nuclear astrophysics and exotic states. Now I'll start with fission studies. We know that if we measure the mass distribution of the products of fission, there is a bump, that means there is an asymmetry. There are two types of masses available, and this has been measured using this old scattering chamber and MWPC with 21 MeV. As we increase the energy around 40 MeV, there is almost no asymmetry, and 62 MeV asymmetry is gone. And this asymmetry is attributed to the cell structure. So what has been concluded in this work is said the nuclear cell effect washes out at excitation energy around 40 MeV. This is the conclusion of this work. Now I would like to show another work which has been done by the measurement of photons or gamma, which is called giant dipole resonance, which nuclear vibrates and produces photon gammas, and it also uses the neutron measurement, because as you see importance of both the measurements so that you can conclude something. From neutron you get the entropy density, which is called S, and from photon measurement you get the viscosity, shear viscosity, which is eta. So what you measure is eta by S, which is a quantity for a collective system, which tells you that about the fluidity of the system. So lower the eta by S, larger is the fluidity. And there is a lower bound, like helium, liquid helium, it has a fluidity of around 1/5, and 1/4 pi, you cannot go beyond that. This is called perfect liquid. It has been shown recently that quark gluon plasma, which is the liquid of quarks and gluons, is having a viscosity of that value, that is around 1/4 pi. And that is also said to be a perfect liquid, which has been created in high energy physics. Now, what our colleagues have found at VECC, that eta by S at this energy essentially is similar to the value which was found for QGP. So what they have said now is that the measured eta by S values are comparable to the high temperature quark gluon plasma, pointing toward the fact that the strong fluidity may be universal feature of the strong interacting of many body quantum systems. Now go to another one, which is a phase transition, which in this case is the SAPE, where the temperature has been measured and there is a bump for a deformed nuclei and not for the normal one. And this has been corroborated by measurement of the photon spectra and neutron spectra, where there is a bump again, which is missing for non-deformed ones. Now this was discussed yesterday also about the Hoyle state. What is Hoyle state? Hoyle state essentially was required. Hoyle conjectured that there will be an excited state in between of 7.65 MeV for formation from alpha to carbon 12. Otherwise, there will be problems. But then what is the structure of this Hoyle state? This is found. This is now nuclear synthesis. This is one of the landmark. But then what is the structure of this Hoyle state which produces carbon 12? Is it linear chain of 3 alpha? Or is it just loosely coupled 3 alpha, or is it a Bose-Einstein condensate? So we have taken series of data for months and years together and collected about 1 million of Hoyle events. And then we have given a lower bound for direct decay, which is important because otherwise the carbon 12 abundance will be different, which is below 0.019 with 95% confidence level. And this is about a factor of 2 lower than was measured earlier. So this gives an insight of this. This is my final one, which is published in Physical Review Letter very recently, which says is that when you make higher mass number nuclei, like in this case gold 183, and this gold 183 not only will have a rotating structure, but it might have a different kind of triaxial deformation, which will be like oblong motion. It's like a top, which is oblong. And there have been detailed calculations done based on the measurements of polarizations and other, and it has been concluded that for this nucleus, there are 2 transverse oblong bands exist. And 2 transverse oblong band has a very important feature which has been found for the first time, is that if you plot them, this oblong energy with the spin, then it goes down for one, which is known. All the other oblong structures which have been found. In fact, it was said that the oblong structure is attributed to this feature. If it goes down, then it's oblong. But what our colleagues have found, that it goes up for the other one, which is something new. And our colleagues, as I said, to explore the horizon, even beyond the VU, which is available at VECC or maybe Peletron and other places, they go to Ganil, France. They go to GIN at Dubna. They go to FAIR, Germany, they go to Grenoble funds, and one of them is a member of the International Nuclear Data Group. So this is our reach of nuclear physics in the international domain. Okay. So now I touch upon another important area is the irradiation study for using our cyclotrons. As we have 3 cyclotrons of different energies, different particles, and when you irradiate materials, we can study the mechanical properties and microstructure, which is core program for our atomic energy, because depending on the dPa per second which is produced, and this is what is the reference for the reactor. So this is what we study. Now what will happen? We have already done irradiation study of RPV steel and Super Ring 42 using VECC beam, and the studies are being continuing. And of course, we have proton, low energy heavy ion, high energy heavy ion, and that creates different kinds of defects or interstitial, and they are studied with XRD, and these are the facilities that we are continuing, and we will continue with medical cyclotron. Now I go to the last topic, which I am personally involved in, which is our participation in high energy experimental nuclear physics. That means we produce either hot quark-gluon plasma or cold quark-gluon plasma, dense quark-gluon plasma. Now, the places where this is because this cannot be done by one institute or even not even one country. So these are the collaborations, international collaborations which happens. So in CERN Geneva, that gives you 5.0 TeV, center of mass energy. Brookhaven, USA, which gives you 200 GeV, and Fair, Germany. So this is the one which is for high density, because the nucleus will be such that they will have quark degrees of freedom, but they will not pass through each other. They will essentially pierce each other and stay there. There will be stopping. And that will be like a core of the neutron star. But when the energy is high, they will just pass each other, and there will be no barrier inside. And it's a pure quark-gluon plasma made of only gluons. Now again, this is my fun of looking at the future, looking at the old. Everything is available in Google. If you now type Rutherford, you will find a paper where the title of the paper is the scattering of alpha and beta particle by matter and the structure of the atom by E. Rutherford FRS. And there is only one author. This is the nuclear physics first paper. This is the beginning of nuclear physics. This is all the other 3 papers where you can find somewhere my name, because I am one of the authors. But then this one has about 15 authors, which is a VECC experiment. This is the first experiment I did. This one is my thesis experiment, which is at CERN, but at lower energy, which is the W98 experiment, about 100. And this is about 400, which is at Brookhaven National Lab. Energy is 200 GeV. And ALICE and LHC, there are 1,000 institutions, 100 institutions and 1,000 authors. So this is not only that the energy goes up, this is the scale of the number of people, the money which is required, because you are looking deeper and deeper. It's inversely proportional. So in this line, this is our collaboration. BCC Kolkata, Science Institute of Nuclear Physics, Institute of Physics Bhubaneswar, Rajasthan University, University of Jaipur, University of Jammu, Punjab University, IIT Bombay, Aligarh Muslim University, IIT Indore, University of Guwahati, NISER Bhubaneswar, and Bose Institute. I have put different color for the HBNI institutes. Now, what do we study in this field of study? Essentially, we study a phase diagram of the strongly interacting matter, unless you increase the temperature or increase the density. When you increase the temperature, then you will go from a phase, which is a confined hadronic phase, to something where quarks and gluons are free. So this is a black and white picture like that you go from here to here. But that doesn't happen like first order phase transition or something, but it has been found that there is a transition and which looks like a perfect liquid. But then when you go to the higher density, like a neutron star, there are more structures. There are maybe different kind of phases, quark ionic phase, superconducting phase, and all sorts of things. Now, how do we access this? If you want to go there, you have to have LHC-like energy, very high energy. If you go in between, just 2 minutes. If you go in between, then you are here. So we have built the detectors since 1994, which is measured the number of photons which are produced in this kind of, these are international collaborations, different detectors are built by different countries. So we have built one which is 1994, and this was the scintillator pads. These are the gas proportional chambers with 85K cells and 200 cells. These are measured photons by pair production, no longer photoelectric effect, makes a shower and gives the signal either on scintillators or gas. And this is the one which is our future experiment where we will take part, and we will go a completely different region where we will handle 10 megahertz interaction rate, unprecedented. Nobody has handled it. All the detectors will become black. So you have to have a new detector, you have to have fast radiation detector, And you cannot just wait to see that interaction happens. You have to collect all and then look everything to computer to do it. This is a technology called GEM, gas electron multiplier, which we are developed at VECC, of course, taken from CERN. It's a gaseous chamber, which is a thin, 50 micron thin polyimide foil with 5 micron copper and top and bottom, and there are holes in between, 70 micron dia, 140 micron pitch. And if you put around 50 volt, and there will be huge field, and the electrons which are connecting will get multiplied. In interesting point, there is no wear, so there is no spark, and the electrons is not connected to the multiplication element. We have built large chambers and then put them in beam in GSI Germany. And as usual, like all of us affected by the COVID, we did a remote shift during this period in 2020. And our guys were in the middle of the night, they were attending the shift duty. Fortunately, the installation and commissioning is over. So all the control and data analysis were done remotely. And when there is a beam, I'll give signal. When there is no beam, this is called off-spill, there is no signal. And there is a nice spatial correlation with another detector built by Heidelberg University, and this is the time correlation. So this is my last slide. So what I have tried to say here is that VECC machines have been delivering beams for basic science research. Major accelerators are K130 and K500, medical cyclotron facility and RIB facilities, which are coming up to be followed by UNURIB. And major nuclear physics experimental facilities are Charge Particle Array, Lambda, Venus, Venture. These are all Gamma, and Penning Trap, which is also coming up. High quality studies are being performed in nuclear reaction, nuclear structure and irradiation, participating in high energy heavy ion collision experiment worldwide. This is an example of collaboration because there are a lot of collaboration words used yesterday. And we are opening up the nuclear physics for superconducting cyclotron and the facility which is coming up for high density research where we'll be using GEM. I could not find time to go more details and there will be looking forward for the high density matter which will be produced at FAIR Germany, which is coming up in 2025. And collaboration is always welcome. Thank you very much.
Thank you for the nice presentation. The session is open for a few questions and discussion.
Thank you, Professor Subhasish, for an excellent presentation, giving an overview of the activities at VECC. I'm very happy to see that the K500 is finally working. I remember in 2002, we had presented our work program at K500, but I was just wondering why only helium and nitrogen are available right now. Other beams are not available?
No, they will be available. You see, sir, there is a problem in the sense, a problem with the, maybe Arup can comment more, but let me put my part, is that problem with K500 is a superconducting machine. And if anything happens inside, and if you have to open the machine, to cooling down itself is 3 months, and then getting up is another maybe 2 or 3 months. And that kills most of the time. And that is what happened as we had this phase. We had some problem with some vacuum. And then we have come up and immediately we started. Now, good thing is that whatever parameters you know from physics, from accelerator physics, you put them and you get out the beam. Okay. So we started with nitrogen. We got the neon next day, and yesterday our director told me that we have got oxygen. So the other ones is not far. So things are under control. That is the main thing which I want to say.
Thank you. Thank you very much.
Just in continuation, I just want to know with the superconducting cyclotron, your experimental facilities, you are also developing new.
Yeah, these experimental facilities which are showed here, these are exclusively in superconducting cyclotron. These neutron arrays and the sky. This is in the superconducting cyclotron side.
Not there in 130 cyclotron?
No, 130 cyclotron, actually the way it is that, for example, you develop something. You take some R&D effort and develop something. Then first thing you have to test it. If there is no beam in superconducting, what will you do? You put some of the modules in room temperature and do some experiment. In fact, one thing I forgot to mention here, I should have mentioned, we have a huge scattering chamber, which is 2.2 meter length and 1 meter diameter in superconducting cyclotron, sitting there, exclusively there, and you cannot move that beast anywhere else. So it's for superconducting cyclotron. You can do time of flight measurement inside the scattering chamber. It's so long. Yes.
Yes, Dr. Chattopadhyay, very good lecture, very well organized. I have several lot of information here, but I have one question. You said that many of your colleagues are trying to avail of facilities in other countries. Now, is it now the facilities which you have at VECC, are the researchers from neighboring countries approaching you and using them?
So that's a good question. So far, I know is that our facility is being used by Indian researchers everywhere. This is very common. But I knew that I cannot, maybe Arup can add, there were some collaborators who is having collaborators in India. And I think Korea one and another institute, they took part in this. Sir, one advantage I'm telling you our facility, that you might know these kind of facilities, that is the cyclotrons which we have, anywhere else in the world, they are almost shut down. Either shut down or they are being used as injector for higher facility. And they do not give facility, this beam of this energy for doing nuclear physics research. And so that way our facility is essentially unique. So I think, in my opinion, I have talked to my director also, that we should have a little bit more outreach outside everywhere to tell about our K500 cyclotron as soon as we have this ready. Arup, you want to add anything to that? Just let me hear from him, and then I will hear.
I can start something.
Yeah, just let's hear from that.
So what he said is right. So we had one experiment from a Korean scientist about 2-3 years back. The system is very much available. So if anybody approaches us, it is very much possible. And just before COVID, one university from UK, they also showed a lot of interest, and they sent a bunch of students to visit our infrastructure and facility. But after that, for the last 2 years, nothing has happened. But in principle, yes, it is very much possible. Everybody is welcome. But we have to go through the regular procedure for foreigners to go through all these processes. But it is possible.
Yeah, but what I will like to suggest, that this is something which should be encouraged. You should see TIFR, GMRT is a facility with many researchers from all over the globe comes there and they carry out experiments. Your facility is now K500, can be a facility which can attract researchers. What will happen is this will raise the confidence of everyone in VCC as students from other countries come and they work there. So just see if you can explain.
No, I agree. I think we will discuss that in our highest board meeting.
Yeah, and my compliments to
Thank
your
you,
lecture.
sir.
It's a very well organized talk.
Dr. Nayak wants to say something.
Yeah.
Last question, because we're
Actually,
running.
actually, sir, I want to add, in TIFR, we have Pelletron. They are in fact foreign, experimenter, they come because we have a gamma ray array, nuclear structure studies particularly, they come.
That's very good.
Yeah,
It's something which we should
and
encourage.
they are also, I'm sure, once things develop,
We go
and then they will definitely come because particularly in this particular energy range around Coulomb barrier, all over the world the study is same. We are contemporary, and if we have a good experimental facility developed, then only people will come. It's very important to have a state-of-art experimental facility.
Yeah, I agree.
So that's a important.
I agree. Okay, so.
Okay, so thanks.
So just I want to thank my director, Dr. Sumit Som, and colleagues who are all online, I hope, for their slides and encouragement.
Thank you, Professor Subhasish. Nice talk. And let's move on to the next talk by Professor Sitabhra Sinha. एक मिनट सर
Okay, so first of all, my thanks to the organizers of this meeting. And it's actually been extremely instructive over the last 2, 3 days to hear about how the various uh, organizations involved with HBNI have been doing complementary work. So I'll be actually talking about one of the areas that the Institute of Mathematical Sciences in Chennai has been involved in. So typically when I say that we do computational biology, there's usually like whoever is listening takes a double take, normally. So as one of my colleagues once said, he often gets this response. So he would talk to someone and then say that, I'm working in this Institute of Mathematical Sciences, and the typical response would be 1 minute's embarrassed silence at the other end, and the person would say, oh, I was very bad at maths in school. And it sometimes, takes us a while to explain that actually the majority of the institute is not mathematicians, but physicists. And so we actually have a very interesting history. Most of you must be aware of this, that the institute actually was founded in 1962. In fact, we are currently celebrating our 60th year. So the way it happened was when Niels Bohr, the famous physicist, was visiting India early 60, he essentially took a tour all across India. And he happened to come to Madras, which was the name of Chennai at that time. And he met with Professor Allari at Madras University and attended the theoretical physics seminar that his students would have in Professor Allari's house. So this used to be a weekly event. And Niels Bohr was extremely impressed by the students. And so when he went back to Delhi, and Jawaharlal Nehru, who was the prime minister at that time, asked him what impressed him most in his India tour, he said, TIFR in Mumbai and these group of brilliant students I met in Madras. And so legend has it that Pandit Nehru called up Professor Allari and asked, what can we do for you? And Professor Allari said that, well, I have this dream. Can we have an institute on theoretical studies at Madras? And that's essentially how we came into existence. So in 1985, we became a CI of the Department of Atomic Energy. And from then on, we have actually spread out in multiple areas. So for historical reasons, higher energy physics used to be the dominant group at IMSc until about the 90s or so. But then Professor Bhaskaran, whom many of you might know, is a very well-known theoretical physicist working on condensed matter physics, especially high-temperature superconductivity. And Professor Simon, who's again a legendary figure in quantum optics, both of them, got IMSc well-known in areas other than high-energy physics. And Professor Bhaskaran, starting in the 90s, started having this idea that maybe IMSc should branch into other areas, especially given that physics has started contributing to biology in a big way. Maybe it would be good to have people who are working in the interface of physics and biology. So starting in the 90s, physicists who kind of work in this interface of physics and biology started coming into IMSc. So my colleagues like Professor Gautam Menon and Rahul Siddharthan and myself, we all were like more or less in the late 90s, early 2000s, we entered the institute. And this actually essentially came up because of this very strong tradition that we had of interdisciplinary work. So, I'll primarily be talking about bio, but just to give you the background, so we have a very lively group working on various aspects of physics. There's of course high energy physics, but more relevant here would be the kind of groups who work on condensed matter, things like graphene and high temperature superconductivity and so on. The very lively group which works on quantum information and computing. And finally, the group which works on soft condensed matter and statistical physics. So in this soft condensed matter and statistical physics group, there has been a long history of people working on problems which originally arose in biology and then, were taken over by physicists and, working in strong collaboration with experimental groups in biology. So in the 2010s or so, we started having this discussion that maybe, we can start thinking of having a dedicated graduate program focused on biology. So in the 11th and 12th plan, the DAE very generously funded projects which involved a very strong, collaboration between biology and physics. So in particular, there was this project for interdisciplinary science and modeling called PRISM, which, among other things, looked at physics of glaciers, physics of climate change. So this was basically spearheaded by our colleague, Professor Shankar. Then there was a lot of work done on fracture. How does material science and physics, how can they be brought together? So fracture not only in like materials for building, but also in bones, like biomaterials, what kind of forces give rise to fracture, what are the mechanisms underlying it. So this is an area where my colleagues, Professor Purushottam Ray, Professor Rajesh Ravindran, were all extremely active. And there was also a lot of work done on biology at the cellular scale. So for example, my colleague, Professor Gautam Menon, Professor Ral Siddharthan, all of them were involved in it. And there was also this IMSc complex systems project. We essentially looked at, what we would now call systems biology, essentially looking at network aspects of cellular and supracellular scales. So we thought that it would be good if we could attract students having diverse backgrounds. So, given that we were primarily physicists working in a physics graduate program, we had students who had a physics background. And oftentimes, people who are coming from a physics background would have, certain preconceived notions about what they want to work on. Like we used to have this running joke that all the students who come from Calcutta just want to do string theory. So, telling them, well, there are strings and then there are strings, like DNA is also a string, right? But sometimes we would find that, it would be easier to have students who come from other background, who do not necessarily have this notion that, certain areas are much more glamorous than other areas. So with that end in sight, we started having this discussion that maybe we could have a PhD program where we can attract students not only from physics, but also coming from other areas like, for example, biotech, or for that matter, chemistry or mathematics and so on, who can actually, work on bio-inspired problems. So with that aim in mind, finally, we had the approval of the HBNI Life Sciences Board of Studies in 2012, and the first students essentially started in 2013. So in answer to this question of why do biology at a mathematical sciences institute, so we often use this quote from, of course, one of the greatest figures in modern biology, Charles Darwin, where Darwin had essentially once said that he often wished he had a better mathematical knowledge because, at least according to him, maths gave a new insight into many of the problems in biology. And I think what modern biology has proved that this is extremely true, given that most of the developments of 20th century biology were spearheaded by people trained in physics like Francis Crick, Max Delbruck, and so on. So what's special about the biology program at the Institute? One thing is that we focus on the theoretical and computational basis of many of these problems. So here we are particularly, fill a need in the Indian science ecosystem there, because there are relatively much fewer Indian institutions which focus on the theoretical biology aspect. And also the so-called bioinformatics programs that are kind of a dime a dozen across many Indian educational institutions, their focus is somewhat different from ours. Oftentimes we find that students who come from these kinds of institutions or trained from these kinds of institutions are more, used to pushing buttons in canned software. They don't really have much awareness of actually what's going on under the hood. Whereas in our program, the focus is on training people where they can write their own kind of programs where they can actually devise new mechanisms for, gleaning truth or gleaning various kinds of patterns from the database of biological sequences. And so, given our diverse faculty interests, like we have people working in computer science, people working in mathematics, people working in various aspects of physics, it's actually extremely useful to have such a diverse collaborators within the institute itself with whom we can talk about different expertise that we need from time to time. And as we emphasize the computational aspect of the computational biology, that's just a tool for realizing all of these interactions. But of course, it's equally important to keep our work grounded in reality. And so there's an emphasis on having strong collaborations with biology groups, not only within India, but also abroad. And this is something that all of my colleagues are extremely involved in, having visits to other institutions which have labs and also have their experimental colleagues visiting us, giving regular seminars, interacting with students, and so on. So we are kind of the newest and kind of smallest group at the institutes, as you might already have sensed. So our faculty strength is currently 5, plus Professor Gautam Menon, who's currently on Lien at Ashoka University. So Sandeep Chaubey is the newest member of the faculty. And of course, Arijit was the first faculty member who joined the computational biology group as such. Where Rahul, myself, and Vani all essentially joined as physicists in the group, but we have strong bio interests. So I will talk in detail about the interests of each of them in turn, just to give you a quick glimpse of people who have been visiting the institute regularly, not only to talk to us, but also to teach in the program. So we have structural biologists like Professor Krishnaswamy. We have Professor Vasudeva Rao from IMSc Tirupati, who's a cell biologist, Dr. Nivedita Chatterjee, who's a neuroscientist, Professor Sandhya Kaushika, TIFR, Dr. Farhad Habib, Costa Sanal, and so on. So coming to the graduate program, I mentioned that we had our first student in 2013. So I'm just showing over here the students who survived the coursework because we actually had a very, very strong program where we essentially weeded out people who couldn't survive the comprehensive, so that we ended up with only the students who are most committed at doing computational biology work. So at present, we have 17 students who are doing their PhDs. And the coursework essentially has 7 core courses, which are mentioned over here, plus 2 to 3 electives, which they have to do within the first 2 years. Among the students who have graduated, so the first student to graduate, Ankit, he went for his postdoc at Wolfsburg and is currently in his second postdoc at University of Freiburg. Devanand is doing his postdoc at Israel, Beersheba. And Chandrasekhar, who's finished just a few months back, is currently doing his postdoc at Harvard. And we also have 2 students who have submitted recently, still awaiting their results. And one of them has already joined as a scientist at a data analytics company in Bangalore. We also have a postdoc program, and our former postdocs are, for example, employed as faculty member at BITS Goa, and one of them is also a scientific officer in our outreach program. And at present, we have postdocs whose background essentially, so 2 of them are from the IIT system. One of them has come for his second postdoc after finishing his first postdoc at Cincinnati Children's Hospital at Cincinnati, US, and the other has come again for his second postdoc after finishing his first postdoc at Dresden. We have, as I mentioned, collaborations all across India. So here I'm just showing a small sample from India as well as abroad. And of course, recently over the last couple of years, we have also developed collaborations with other institutions within the HBNI fold, thanks to some of the meetings that we have had just before COVID broke. Among the various meetings and workshops that we had organized over the years, so our flagship meeting event is a series of meetings we have had on modeling infectious diseases. This is, of course, way before we even dreamed that something like COVID could come about. So in 2006, we had our first workshop on modeling infectious diseases, followed by one in 2010 and another in 2015. And many of the people who actually came here are currently involved in COVID modeling, for example, in the United Kingdom. So we had, Dr. Sebastian and Dr. Edgar Delgado Eckart and so on. So all of them are actually extremely actively involved in the COVID response team of the United Kingdom. And so this kind of proved to be a very good, training and a training event to basically make students familiar with modeling techniques in epidemiology, something which would be a very good resource building for making the country ready for the next epidemic wave, for example. Apart from this, we have also had meetings in, for example, molecular motors, regulatory epigenomics, biological networks, and so on. So the current research interests span a whole range of scales, going from computational genomics to biophysical modeling, systems biology, ecological modeling, computational neuroscience, biomolecular simulations, infectious diseases, cancer research, and organelle biology, with publications occurring in many high impact factor journals. And it's also received a fair share of media interest with the results of the faculty members appearing in for example, newspapers, magazines, and magazines focused on the things like Physics Today and so on. All right, so let me, in the remaining short time, talk briefly about the research interests of the various faculty members. So Dr. Sandeep Chaubey, who is like the youngest member, as I mentioned, his primary interest is looking at how do cells make decisions about what they want to become. So, we are all familiar that, when we are young, we have certain dreams of what we want to do. And, as we grow older, because we can't qualify, for example, JEE, certain avenues are close to us. We can't get into medical, certain avenues are close to us, and so on. So we find that over time, what we can become, that gradually becomes more and more funneled, right? Very similar thing happens with cells. So every cell in our body has the same genetic code, right? So in principle, any cell can become anything, right? So when you're born, you could become a kidney cell, you could become a liver cell, you could become a brain cell. But that's not typically what happens, right? I mean, you don't expect a cell which, let's say, occurs at your toe to become a nerve cell. If that happens, disaster, right? So how do cells decide what to do, and you don't have all kind of chaos ensue? So you have a series of what we call bifurcation events, where a cell has to decide between, let's say, becoming a progenitor of a nerve cell or a progenitor of a muscle cell. So once it takes that decision, it cannot really go back and then say, no, I made a mistake, I want to become a liver cell. But once it crosses the checkpoint, in some sense, your future is kind of constrained. So then, you go to the next checkpoint and maybe you decide, do you become, subtype A or subtype B? And then you go to the next checkpoint, do you become subtype X or subtype Y, and so on. We still don't completely understand how all these decisions take place in such a way that you don't have, as I said, liver cells occurring here and kidney cells occurring here. So we really like to understand this better, because when this doesn't work right, all kinds of disabilities and life-threatening disorders can arise, as you might well imagine. And so Sandeep works on things like, for example, how cellular organization is guided by processes like phase separation, where proteins essentially bind on DNA, and essentially they form clumps or clusters which act as reaction chambers. He also tries to understand how is it that physical processes leads to this interesting things like, endoplasmic reticulum or mitochondria forming. So mitochondria is essentially, as you might remember from, school biology, the factory, the powerhouse of the cell. And we would really like to know what are the physical processes which lead to formation of mitochondria, because that's essentially one of the ways in which biology made this enormous leap from single cell to multicellular organisms. Without the mitochondria, we would still have been swimming around as single cell bacteria. And as I already mentioned, going to look at how cells make their decisions about their fates, and also looking at things like, for example, gut microbiome, which of course is extremely important for keeping our immune system up to speed. Arijit Samal works on a multiple range of topics. Just a glimpse of those. So he works on, for example, network biology perspective on chemicals which are relevant for drug discovery and toxicology. And one of his, extremely important discoveries or work has been working out the complete phytochemical space of Indian medicinal plants, something that has got a lot of media coverage. So he has this database called IMPAT, in which he has essentially put together all the medicinal plants which are part of traditional Ayurvedic practices. And this database is, of course, freely available to all scientific researchers. In addition, he's also been looking at things like endocrine disrupting chemicals and systems modeling of metabolism and protein secretion in microbes. So, this is basically just the details of what I just mentioned. In addition to this, he's also looking at methods for analyzing complex biological network and how to do network analysis of experimental data sets which come from various experimental labs. So, for example, he's been looking at proteome and phosphoproteome data sets in Mycobacterium tuberculosis, which are developed, which are essentially worked at in the CCMB and ICGB, and also regulatory network analysis of the Mycobacterium tuberculosis, which is being investigated in IISc. My colleague, Dr. Vani Vemperla, is using molecular dynamics to study membranes. So essentially, in an analogy, you can think of the cellular membrane as something like the border security force or the CISF, which is working over here. So the CISF is constantly on alert for possible malcontents or miscreants who might be trying to get inside vital areas and do some mischief, right? So cell's membrane has a very similar job. It's essentially protecting what's inside the cell from things which are outside. So all the time, malcontents like pathogens, HIV, or for that matter, you could think of COVID virus and so on. They're trying to get inside the cell and do their stuff, right? Which is not very good for you if they manage to get in. So the question is, how does the membrane keep track of who are the malcontents and who are not? Because you can't just let anybody in, but at the same time, you can't just seal off the entire cell from the outside. At that point, you also want to have your genuine workers coming in, right? So the cell needs fuel, the cell needs all kinds of, the cell needs to get some sense of what's going on outside so that it can respond appropriately. So it also needs to have some kind of responding to signals outside. So it also needs to let people in, but it needs to let people in selectively. So how do the membrane of the biological cell work out what is a pathogen, what is not, how does it interact with various kinds of important molecules? Like, for example, when an anesthetic molecule impinges on the cell, how does the cell bind it, and how does that lead to essentially the behavioral changes like sleep and so on? So she's been looking at recently this viral peptide interactions with cell membrane. So for example, if you look at hepatitis A virus peptides, when it impinges on the cellular membrane, what exactly happened? How does the pathogen manage to get in under certain circumstances inside the cell and create havoc? So this is something that she's been working on using molecular dynamics. My colleague, Professor Rao Siddharthan's focus is on the genetic code. So we all know that, in some sense, the DNA is the instruction for building the cell. So you ask anyone, okay, where are the instructions? Where's the program? They will say DNA. Okay? But what is left answered over here is that if that's the instruction, every cell has the same instruction, right? So as I already said that, some cells will become nerve cells, some cells will become liver cells and so on. So that means even though all cells have the same set of instructions, a particular given cell is only going to use some set of the instructions, others are going to use another subset of instructions, another cell is going to use another subset of instructions, and so on. So how do you make sure that liver cell would look at, instruction A, B, C, nerve cell would look at instruction X, Y, Z, and liver cell would look at instruction D, E, F, let's say. So that means there's a lot of regulation going on which part of the DNA do you read at any given time. And this, of course, has to be self-organized because there is no master operator on top of the DNA which kind of decides, okay, you are a liver cell, you only read these instructions. You are a nerve cell, you only read these instructions. So that means you have to have some kind of a network which says that if instruction A is being read, make sure that you will never go on to read D, E, F. So the moment the cell starts reading certain instructions, other instructions would immediately be locked to it. So you need some kind of a control mechanism to allow this. So Rahul kind of works on that, and he's also been extremely involved in recently using big data techniques and probabilistic learning to look at problems of health and disease. But just to mention his regulatory genomics work, so he's been looking at how transcription factors, so these are the proteins which essentially go and bind to areas of DNA, which will allow or prevent reading of certain instructions. So in collaboration with other scientists, he's been looking at how different transcription factors interact with each other. So this could be cooperation or this could be competition, resulting in reading or not reading of various instructions, which leads the cell to adopt certain particular configurations. He's been looking at things like chromatin and East centromere. And in the other aspect of his work, he's been looking at how using machine learning, he can actually make a difference to healthcare. And in this, he's been involved in a number of multidisciplinary teams, for example, which includes Dr. Paul Ramesh, who's a very famous doctor in Chennai. What they look at are, for example, looking at the patient data sets, trying to figure out what are the critical parameters which decide whether a patient will survive a particular stage of the disease. He's also been involved in looking at risk factor for children. So, looking at the size at the gestation period, asking whether this might lead to complications as they start growing. Other projects involve gestational diabetes and postpartum diabetes. He's also looking at, so this is actually a collaboration that he's having with BRC, where he's looking at differential gene expression on radiation exposure for individuals from normal and high background radiation histories. And, among his biophysical interests, he was also looking at the CDCM, which is a multifunctional DNA binding protein. Okay, I'm kind of almost out of time. I'll just take probably a couple of minutes to mention my own interests. So I look at networks. I already mentioned, why networks are so important in biology, because they are the ones which essentially decide what kind of decisions cells take. Patterns, so patterns are, as we grow up from a single cell to this, extremely large number of cells that is right now speaking to you. But it's not just a formless, mass of disorganized cells. There's a very specific form that all these cells kind of gather into, which kind of immediately identifies myself as a human being. So what is it that, allows all these cells to somehow aggregate together to form this very characteristic human shape? So these are the kind of questions we are interested in. And of course, we're also extremely interested in understanding how these kinds of networks and patterns can have significant role to play in deciding whether we are attacked with certain diseases. So we are very interested in, for example, brain activity. And just to connect with an earlier talk by Professor Divakar, just wanted to mention that we've been looking at how brain activity, or rather the synchronization of brain activity, changes as a result of fatigue. So we find that essentially a very, very strong synchronization of activity in various brain areas is correlated with the subject actually becoming highly fatigued and eventually going off to sleep. So this could be possibly used as a marker for, fatigue or indicating fatigue in subjects. We've also been looking at, how to use big data for identifying early markers for cognitive dysfunction. And here we've been working with an NGO called Didara Children, who have developed a web-based educational package where children essentially click the right and wrong answers for various tasks. And these are like preschool children. And by using these answers, so here's a database for like all the answers given by children and how long they took and so on. So by using this, we essentially tried to diagnose learning disabilities in preschool children, which is kind of not very easy to do using other kinds of markers because they're still too young to, for example, subject them to various kinds of psychological tests. We're also interested in, for example, arrhythmic activity in uterus and the heart, which are in some sense complementary problems. In the heart, the problem is like if your heart kind of goes into mode where different parts of the heart are doing different things, it will lead to cardiac arrest. And if nothing is done, of course, you will die. In the uterus, it's the opposite problem that, sometimes if the different parts of the uterus just before the child is born decides to start doing essentially the same thing as their neighbor, you get premature contractions, and that's actually the #1 killer for children. So it's the leading cause of infant mortality. So our job over here is to understand what leads to this collective transitions so that we can prevent either death due to cardiac arrest or in the case of infant mortality to prevent premature contractions. We've also been involved in, for example, cancer biology, where we are collaborating with Cancer Institute at Adyar to come up with markers for indicating like which factors actually decide whether the treatment would be successful or not. We're also looking at how immune response is shaped as a result of exposure to various factors. And just to end, and because it was mentioned in multiple talks yesterday that DE might find it very useful to come up with a mathematical description for how people respond to various kinds of stimuli or inducements, how to model crowd behavior, how to model individual behavior. Let me just indicate that we've been involved in actually doing this in the context of epidemics, in particular COVID-19, where we are trying to understand how policies and the way people respond to those policies interact to shape epidemics. So this has, of course, immediate impact on understanding why a lockdown would be successful or not, but also to understand things like vaccine hesitancy. You have a vaccine for a particular disease, but that doesn't necessarily mean that people will go out and, get themselves vaccinated, as a problem that we well know. And it's not just true for COVID vaccine. If you look at US, it's a developed economy. They don't have an excuse that vaccine is too expensive, right? And yet we have had large measles outbreaks. Measles, right? You have a vaccine for measles for the last 25 years. Why are they having measles outbreak in, 2019? And that's because a large number of people have decided to voluntarily opt out the children from having measles shots. You might say that's crazy, but people do such things. And you can actually try to understand why people would have inducements to do these kinds of things. So we essentially couple models for studying how epidemics spread with models of how individuals take decisions, whether to be vaccinated or whether to comply with lockdown rules, whether to wear masks or not, whether to go out when the government has specifically forbidden them from going out. And in doing these kinds of models, we can actually reproduce many of the features that we see in reality. So for example, we used a model of people complying with lockdown mandates, and we found that actually if you have even a small section of people deciding to not do the full lockdown mandate, you could have, for example, very particular kind of multiple waves in the disease incidence, which kind of mimics roughly the way you had multiple waves coming around in India, for example. So this is the model, and this is actually what we saw in India. So this is the first wave, there's a second wave, and this is the extremely brief period in September last year when we had what I would call a third wave, even though what the media called the third wave occurred much later. So you can actually reproduce many of these features using these kinds of models. Okay, so I'm done, and I'd like to thank you for your attention. And again, I'd like to thank the team organizing this meeting, and I really look forward to having more collaboration within the wider HBNI scientific ecosystem. Thank you.
Thank you, Sitabhra, for a very nice presentation. Now we have time for a few questions.
I was curious to know whether you are interacting, maybe you are, I'm not aware if the recent work, interacting with the material science group of IGCAR, because they are looking at the signals given by both brain and heart through magnetoencephalography and magnetocardiography, and but examining a variety of population in collaboration with NIMHANS, etc. So you were talking about onset of diseases and things like that, how they can be modeled based on signals from the body. Whether any interaction is there with regard to modeling these things based on the data they get. They get a patient profile and they also get the signals from either heart or brain. Will that be of interest to you? I don't know. I just wanted to mention.
Yeah, actually, I was talking to Professor Divakar during the break because I was very curious as to what kind of work they're doing, and it seemed like definitely some kind of a collaborative work can be done because we actually work with a group at Calcutta University who are doing a very similar kind of thing. Like using a mesh net of 16 electrodes and basically getting the EEG data set from there, and then we do the analysis. So in principle, actually, we could very easily set up a collaboration.
It's entirely a different question. So what is your take that any other peak will come about the COVID?
No. So I mean, we are not into this forecasting business. As I keep telling everyone, it's virtually impossible to say, so much in advance that whether peak will come because there are so many unknown factors, right? So it's basically impossible. But what we are primarily focused in understanding is what are the factors which make such waves possible, so that you can make policy decisions. So our work is more at shaping policy rather than trying to predict.
Thank you.
Indeed, it was a very nice presentation, and
Thank you.
in fact, we could appreciate some of this. What you talked about using biological systems and learn. I have one specific question. In terms of, and this is a problem that we are also looking at. We are looking at analyzing human behavior in the context of that whether he could be an hostile. So even if I look at a crowd and looking at this behavior of this crowd, trying to analyze that what could be this behavior. So what is your take? Is this technique somewhere could be actually used in this context, analyzing behaviors, looking at his actions over a period of time?
Right. So extremely good question. So see, there are two ways we can try to understand behavior. One is the behavior of a person when that person is taking some decision in absence of any particular influence from his or her peer group. Okay, so a crowd is the other extreme, where individual essentially is not really making a rational calculation of benefits and risks, but basically is being carried along by whatever is happening in the immediate neighborhood. So the way we analyze these kinds of behaviors kind of also calls for different kind of mathematical tools. So when we look at, like, for example, vaccine decisions, which presumably you are trying to take a decision in the quiet of your home, and you're asking, okay, should I go because I have heard that this person died the next day after taking the vaccine, so is there some risk for me? Or for example, if it's a case of childhood vaccine, you have heard stories that maybe this vaccine makes autism much more likely for my child, so should I? And back in your mind is this thought that, look, if everybody takes this vaccine and I'm the only one who's holding out, it's
equal, right? So, everybody's taking the vaccine, so I have very little risk of getting the disease. So why carry this small risk of having some side effect when anyway I'm protected because everybody else is having the vaccine? But of course, if everybody else is having exactly the same idea, then essentially we have this case in US where large parts of the country is essentially now completely unprotected because many people thought they were being very smart and decided to not have their children being vaccinated for measles. So the mathematical technique of game theory turns out to be a very good way to model this kind of thing where individuals are trying to take strategic decisions, balancing their cost and benefit, whereas crowd behavior is more, akin to, for example, I keep saying like the even spin model that we are very familiar in physics, right? So where you are doing something because all your neighbors are doing the same thing. So basically you are following fashion. Okay, so there it's not so much game theory, but more like the collective models we are more familiar in statistical physics, which might be a better model. So it all depends upon what's the context in which we are studying this.
So maybe we would like to discuss more on this.
Sure.
Yeah, there's a question from chat box. This is from R. Ganesh from Gandhinagar. I see there appears to be no work on evolutionary biology and its computational modeling. The question.
So I know that Rahul has been working on evolutionary phylogenetics. So if you are interested, I would definitely want to put you in touch with my colleague, Professor Rahul Siddharthan. So he's been working on, some aspects of, how gene sequences, for example, evolve over time.
Yeah. May I just one question? I particularly enjoyed your lecture because you were able to connect with a person who is neither a physicist nor a biologist. So that was one interesting. But then my curiosity was piqued as a physical metallurgist. In two of your slides, one to do with the cell speciation, if that is the correct word I've got, that is how cells specialize. And in the other one where you talked of pathogens or other things attacking at cell membranes. In both of them, you talked of phase separation. Now, phase separation is a well-known, heavily studied physical metallurgy phenomena where you have two phases emerging out of through some compositional modulation or other mechanisms. There are various mechanisms, including spinodal and all that. So are there any parallels between these diverse fields? That is there a kind of cell phase separation through compositional modulation or some such thing happening in cells?
Sorry, phase separation through?
Through compositional modulation or any other such mechanism is known how this occurs in cells.
I'm not very familiar with this because this is a work that primarily is being done by Vani. But I can certainly put you in touch with Professor Venkarala so that you can have more details on this. Yeah, but phase separation is something that all of us are very interested in. So what are the ways in which you have multiple phases occurring, and how do we segregate these phases and so on? So it occurs in my work, it occurs in also Arijit's work and so on.
Yeah, in fact, I had shown something in vanadium alloys on that.
Sure.
So we are running out of time. Let's thank Professor Sitabhra. Also thank all the speakers of both the morning sessions. Thank you.
Thank you, Professor Ravindran. With this, we draw the scientific sessions to a close. To mark the conclusion of what turned out to be a forum for excellent scientific discussions, we will now hold a valedictory ceremony. Let me first acknowledge the presence of eminent chief guest of this valedictory function, Professor R.V. Grover, Founder Director, HBNI. I now request Professor Vasudeva Rao, Vice-Chancellor, HBNI, Professor D.K. Maity, Associate Dean, HBNI, and Professor A.K. Dureja, Associate Dean, HBNI, to escort our chief guest to the dais. I now request Professor D.K. Maity to kindly deliver his welcome address.
respected Professor Grover, Professor Vasudeva Rao, Professor Dureja in the dais, and professors and other participants in the auditorium and online. Welcome you all to this concluding session. This meeting was conceptualized about a month back. Then we have discussed with Director BRC and many other professors like Professor Tagi, Professor Yusuf, Professor Kannan, Professor Banavali, Professor Prasanna, Professor Sulekha Mukhopadhyay, and Professor Vedangas Mohanty to give the final say of this meeting. We have tried to make this meeting, as you have seen, very informal, as it's a meeting of our family, HBNI family. I'd like to mention that MHRD has also instructed all the IITs to have a similar exercise. Soon they're going to hold it. In 10 scientific sessions, our faculty members has displayed their engagements in almost all possible research areas related to basic science, engineering, and health sciences. Research areas span from single molecule spectroscopy to cosmology and sub-femtosecond time domain to basic science to time domain of about 20 years in health sciences, in addition to mega facilities like accelerators, lasers, and nuclear reactors. And on the other, we have seen some of our faculty members are engaged in international collaborations in large projects where several countries are involved. On the other hand, some of our faculty members are working in silo. HBNI has taken this initiative to bring all our faculty members for possible research collaboration as well as running academic courses involving faculty members from different campuses for more effective education and research through such HBNI initiatives. Of course, we could not include art sciences, and probably in the next meeting we'll include art science also, and more interdisciplinary research will emphasize on that. We'd like to listen to you how to go ahead, maybe through a baby steps to start with. I'll end citing one daily life example of applications of basic science. As we have talked about basic science, using GPS for location. If we do not consider Einstein's theory of relativity to add correction to GPS system, the error of location of this auditorium may be tens of kilometers. Probably the GPS would have located this auditorium at Kharghar Golf Course in place of few meter accuracy. Thank you all.
Thank you, sir. I now invite Professor Vasudeva Rao, Vice-Chancellor HBNI, to the podium to talk about the way forward.
Professor Grover, Professor Maity, Professor Dureja, and other senior faculty members who have joined this session here as well as online. I join Professor Maity in welcoming Professor Grover as the chief guest to address the gathering in this session. I have to recall that it was Professor Grover's efforts that gave shape to the concept of HBNI. As the founder, the first director, and the first vice-chancellor, he has created and nurtured this ecosystem which has now brought us together here. On my part, I wish to take just a few minutes to share my thoughts about the proceedings of this meeting. When we started the discussion on this program in our academic committee, we had a bit of hesitation on two counts. First is whether a meeting with faculty from all different disciplines, from all different centers, is it going to get the response that we wanted? Second was about the format of the meeting. We had several questions like whether we should have had all physics presentations together, all chemistry together, and so on. And finally, of course, we decided to experiment on both counts, and I'm happy that the proceedings of the last few days established very clearly the great enthusiasm in the faculty in all our CIs to share their perspectives with mixed audience. I must compliment all the speakers for tailoring their talks so that they can convey the essence of what their institute is doing and the research infrastructure available. And I'm sure that this will go a long way in establishing interdisciplinary collaborations in future. I am also confident after listening to the talks that within the institutions under HBNI, we have such strengths in various disciplines that we can undertake and resolve any technical issues that may be faced in the mission programs of DA. Now, what is the way forward? I want to talk about the 3 steps. First is that we have already planned to follow up this meeting with the discipline-specific meetings. We plan to organize an exclusive meeting of physics faculty very soon, and this will be followed by meeting of faculty from other disciplines as well. The second step is to look at important domains where there are strengths in different CIs and bring the faculty together to share and collaborate as a facilitator. In this meeting, we could see several examples of such topics. Just to give one example, we could see the great interest in cancer immunology at NISER, and this also happens to be a thrust area at ACTREC. Another that could benefit from collaborations is the quantum information science and technology, where several institutions, including HRI, IMSc, NISER, DRC, they are all involved. HBNI is in a unique position to facilitate collaborations between these institutions, and more importantly, for the country to offer courses and research programs of high value by combining the strengths in all these institutions. Not too far in future, I expect to see credit courses or research projects being offered in which the students interact and get mentored by faculty from more than one institution. Equally important, or more important to me actually, will have to be the bilateral or multilateral meetings on specific topics where multidisciplinary approaches will be required. And many topics could be recognized from the discussions in this meeting. One example was the development of materials and processes for implants to treat breast cancer, where the medical community can engage with specialists in additive manufacturing to reap very high benefits. Topics like reliability analysis or even probabilistic safety assessment for reactor systems could perhaps be more effectively handled through the joint efforts of engineering as well as mathematical faculty. I'm sure that there are more examples. Because of lack of time, I'm not giving any details. I'm just trying to show 1 or 2 examples of what I have observed by listening to the presentations in this meeting. HBNI will be happy to receive any suggestions on such meetings of either discipline specific or domain specific or problem specific. We will provide all the organizational support. Another important outcome of this meeting is a concern or enthusiasm for sharing of resources. Now that the faculty have better appreciation of research infrastructure available in different institutions, the range of problems that they can study, I'm sure, will be widened. And also, such sharing of resources will be more effective and economical in the long run. When I was talking to some faculty during the meeting in the last few days, and when I listened to the presentations today from VECC also, one could see that some people brought up actually the possibility of computational resources being shared across the institutions. If we can be part of a grid computing network with other countries, can there not be a grid computing network within HBNI CIs so that each institution doesn't have to take the steps for establishing high-end computing facility involved with the civil infrastructure, manpower, and frequent refurbishment and so on and so forth. This is I'm just leaving a thought. Maybe already it's under discussion in DA. I'm not aware. I thought it's a topic which emerged here that we could definitely, through sharing of resources, make much more effective contributions. Before I conclude, I wish to convey my sincere thanks to directors of all the CIs and OCC who not only provided full support from day one to the organization of this meeting, but also actually physically participated in the meeting, chaired sessions, and held discussions. Many faculty and directors of CIs have also come forward to support this initiative of discussion meetings by coming forward to organize future meetings in different venues. And this augurs well for the collaborations. And today's visit to BRC facilities and the visit planned tomorrow to ACTREC are also bound to add further momentum to the thought process for the collaborations. Before we invite Professor Grover to address the gathering, I'm sure that some of the senior colleagues here, directors from CIs, may have a few thoughts to add to mine. If anyone would like to come, I would like to invite them. Professor Gautam.
Hello. I have been in many meetings over the last 30 years. I can't recall any other meeting like this where I spoke to quite a few participants and everybody said, this is a very useful meeting. Okay, I mean, I heard comments like, this is a very interesting meeting. Some said, no, it's not so interesting. Things like that in the previous occasions. But here, everybody I spoke to told me it has been very useful. It's not exciting or interesting, it's useful. That is the takeaway for me. Now, before I come to the context of what I learned, I mean, as in the present role of administrator of an institute, I would like to draw an analogy with an episode in history. There's it's about how many years back? In the 1940s, okay, in a conference in 1947 in New York, it's a Shelter Island conference. The formulation of quantum electrodynamics was chalked out by two people, okay, under the supervision of Oppenheimer, who was the organizer of the meeting, by two geniuses. One was Richard Feynman, the other was Julian Schwinger. Now, they are both from New York. But the way Schwinger did it, I mean, starting from the scratch all the way to the proof of renormalization, was very laborious, the way, traditional way of calculation, computation. You know, most of the people didn't quite understand it. Enrico Fermi took a long note so that he could share it to the students and we'll come back and, discuss it. Feynman did it in a different way. Well, today we follow mostly the Feynman approach, but at that time it was like magic. It was like smart, what should I say, cheating that many people thought in the traditional school. And completely independently, in Japan, Tomonaga also did the same thing. So there were three different people talking in three different languages. Okay? The community needed someone who will bind the three in one thematically unified approach so that the rest, the high energy, the theoretical physics would proceed according to that path. That was Freeman Dyson. Dyson's role in interpreting all of them, that convincing the community they're all speaking the same thing, was no less important than any three of them. We are indebted to Freeman Dyson as ever. Now, coming back to the present context, as a theoretical physicist, it's not that I understood everything, but one thing I understood, when the presenter from one institute is talking about instruments and experiments, be it in physics or in biological science, he or she may not know what is going on similar things that his colleague in other institutes are doing with a similar or somewhat different experiments with using somewhat different instruments, two different languages. Maybe in this kind of meeting, when they're talking to each other, they can see a lot of similarity, complementarity. So what Freeman Dyson did to quantum electrodynamics, this kind of forum can bind many people together. And when you add things, it's not some of the individuals, as you all know. 1 + 1 is not 2, more than that. If it's not 11, it is at least more than 2. So I'm sure what Professor Vasudeva Rao mentioned, there will be many more meetings, there will be more satellite meetings. And next time when you come back here, we should also have a session where we can, people can report on the developments following this meeting. I mean, what happened in between, what kind of new collaborations have come up. And it is also important, and it's not just two people from two different organizations putting their names on the same paper, and that's the only purpose of the meeting. There is also a, in the socio-scientific need of having to join our forces together. While we try to appreciate our strengths, we should not underestimate our weakness. Like, it's not that, this is the first time we get to see you. This is the first time we are talking for a particular purpose. Particularly in the, let me not be too diplomatic. Let me put it in a very, harsh way, that I have seen, at least among my colleagues who are using expensive instruments, they're trying to possess those instruments as in an obsessive way, as if, to share it will reduce their credibility in the long term. Let me tell you, what we learned here is that, if we share, both of us will prosper. You will prosper in your own way, so that I will also prosper in my own way. So that, this is an opportunity to share and prosper together. So I have three takeaways. Like, next time when you would write the DPR for the next plan project, at least for me, I would look back into the list of things that you have. Okay, how much they are used. I'm sure that, we may not get the amount of money we would ask next time. I would at least be prepared to get much less than what I would expect, and then I have to optimize. So in that case, I will at least look into the treasures that you have, get back to you, maybe under some forum, and see how we can share the things. I'm sure you will have the same experience as I have. All institutes will face some kind of a, it will be similar problem, and perhaps under the HBNI umbrella, we can sort out our differences. It's not the us and they culture. We have to coexist, and in order to establish our credibility as a community, first under the DAE, HBNI umbrella, then on a larger scale, to be responsible to the fund giver, to the society at large, we have to re-establish our credibility, perhaps. This is number one. Number two, the experience that we gather here may be relevant also for the next course of hiring. Sometimes some brilliant guys write to us that we would like to, apply to your institute, but we need machines like this. Quite often, we cannot reciprocate in a positive way because we don't have this instrument. We may not be rich enough to provide that instrument in a short term. So that in that case, I would, this is a good opportunity to communicate to you. If I know that in some other institute, in some other organizations, something similar exists, which is not used in full capacity, I would not say underused, but not to the maximum potential, then I would write to you that can we, do something together. So this is number two. And regarding the students, often the students come to me and say that, sir, I cannot, in the last few months, I'm going through a difficult time because the instrument on which my PhD thesis is based is out of order. So if something similar exists in your institute, I'll get back to, I'll talk to you and say whether, for some time, we can share the students because they're all HBNI students. Okay, this is happening. I'm not saying that this is not happening, but if it happens in a more structured way, in a more formal way, we can address all the three things together. Okay, so the faculty, the students, as well as the resources for optimal use. That's all I want to say, and I would like to, thank the organizers, Professor Vasudeva Rao and his team. And as I told you before, that I'm looking forward. This is only just the beginning. I'm looking forward to many such meetings in a somewhat different format every time we meet, depending on the need of the hour. Thank you very much.
Thank you, Professor Gautam Bhattacharya, for your very important remarks. Anybody else would like to speak? Professor Panda? Yes.
Respected Professor Grover, Professor Vasudeva Rao, Professor Tripathi, Professor Dureja, and my other colleagues, including directors, faculty members, students of various constituent units who are being present here. I'm sure you are all feeling hungry and we are waiting for the chief guest to speak. And most of the things have been spoken by Professor Rao as well as my friend Gautam. So I'm not going to repeat them. So first thing I would like to say that for last 2.5 days, as chairman or as speaker, we are telling thank you, Professor Rao, etc. I think now the time has come. We should congratulate Professor Vasudeva Rao and his team for organizing this meeting. At least I have only a few more days to tell bye to the system. And I must say that this meeting was unique and I have never attended meetings earlier like this. In fact, worst thing is to happen in a DA meeting only on symposium. So they put morning hour, this topic, afternoon, this topic, etc. And generally my observation was that if you are working in phenomenology, what is called phenomenology, low energy science, most of the participants in the audience will be only from those people. If the afternoon session is string theory, most of the audience will be in the string theory group. So what is the difference there from here is it's not only physics, engineering, chemistry, biology. Okay, some people because of their flight and things might have left, but most of the people are eager to listen what's happening not only in other CIEs, but who is doing what. Because most of these speakers presented the details of research going on, both theoretical and experimental in their institutes. So we had a glimpse of that. And there are some questions which are being asked, and I could see that in even the last talk, I found that someone from material science is trying to prove that whether he can use how to do the modeling in the biological modeling through computer science, etc. So this really provides us a platform. And I will say that these are much more meaningful and gives me, a person like me who works in string theory, to meet a person who works in medical science. And yeah, I think someone told that these are any string theory, and DNA is a string theory, and this is a lighter side. But this is unique, and I've not even heard of that it ever existed anywhere else. And that's where I congratulate HBNI to conceive this idea. I've been talking to the Vice-Chancellor that next we'll plan subject-wise, but will not make it subject-wise, like say physics. Along with physics, if there are interdisciplinary subjects with physics, as he heard that some of the biology are there, we like to combine them. So it will be more effective. And similarly in other subjects. In fact, that is the main reason I am trying my hard, and soon I will possibly get the good news that I am taking a TMC center to the NISER campus so that clinical doctors and biology people together can collaborate and interact. We should not keep our observations in the laboratory and write a paper which will publish somewhere and go into library at the end. What exactly we do if we are talking in a daily basis or weekly basis to the clinical doctor who are interested in similar problems, that will be more useful. They can use it immediately. And so we are trying that. Professor Grover, I think, is in the committee of AEC. I think that is in this month, this proposal will come, which has been already cleared by the PMC council, etc. So we'll like, so just let's consider 10, 15 years ago. I don't think any scientist was talking to any doctor. But now you see that what is happening. The areas has come narrowed down so much. A scientist, a doctor, a scientist, when I say a physicist, a chemist, a computer scientist, all of them are standing in the same platform and trying to sort out some issues. And we all know we can't clap in one hand. We have to have at least 2 hands to clap. And if you have more people, like in the audience, when I told congratulations now, no more thank you part is over. So we could clap, which could make a noise. And I'm pretty sure in that direction, if all the stakeholders, all the minds who are thinking of issues can talk to each other and join, not only HBNI, our national club. Thank you very much.
Anyone else? Anybody else would like to make a Professor Tiwari?
So thank you, sir. Initially, it was for directors of CIs, so I got a bit impeded, but thank you for encouraging me to come here and share a few words. So I join everyone to compliment the organizers for this event and to congratulate the organizers, in particular to you. It has been a very satisfying event, and I won't spend time in telling that, but I want to make a very, very small, probably a significant suggestion for some events which may happen in the future. So, Department of Atomic Energy consists of R&D centers and along with industries. So like NPCIL, Heavy Water Board, Nuclear Fuel Complex. So what I have seen in the last several years, I have been understanding HBNI better and better every day, so including yesterday. So what I have seen has also emerged from the various talks that in some manner, although the problems of interdisciplinary nature have been taken, but the applications have remained localized. So like BARC is working on its problem, but within BARC, on its reactors or on its chemical plants or on its reprocessing plants, etc. Similarly, IGCAR or RRCAT, etc. I'm talking about mostly on the engineering or those on the interface of science and engineering. So if we could create some opportunity and invite in our next these kind of events, these reps of our industries who come with their research problems. I'm not talking about day-to-day problems related to safety, etc., but the research problems. And they share the research problems on this, I use the word, big platform to create opportunity. Such a platform did not exist. I did not see this kind of thing. There might have been small debates. I have myself and a lab which I was having in E&I, we have worked a lot for NPCL problems, but then HBNI can probably create a bigger forum for working on their research problems. We have seen that with the application of data-driven methods and identifications, I'm not talking about the application of high-end mathematics, high-quality mathematics, very, very basic mathematics, but I'm talking about some simple mathematics like differential equations, difference equations, statistical methods, these kind of things. They have helped to improve safety, reliability, accuracy of control, and economics in the area of space, aviation, and chemical industries. The same thing can happen to nuclear industry also, nuclear reprocessing, nuclear fuel fabrication, and our heavy water production and special material production also. So this will be my suggestion, and probably we can open gates to this kind of a big collaboration within DAE, between R&D and industry on the platform of HBNI. Thank you, sir, for giving this opportunity.
Thank you, Professor Tiwari. Any? No. Anyone else would like to speak? I think we are also running out of time. If there's no person from audience, maybe we will proceed with the program.
I thank all directors of CIs and Professor Tiwari for their valuable viewpoints. It is now time for the valedictory address by our chief guest. So please join me in welcoming Professor Grover to the podium. Please, sir.
Thank you, Professor Vasudeva Rao and all distinguished colleagues. Physical meetings have resumed after a long gap, and it's a pleasure to see real people. Seeing images on the screen is not the same thing as meeting everyone in person. So I must compliment Professor Vasudeva Rao and his team for organizing this meeting on a topic that concerns all of us, irrespective of the discipline one belongs to. The main reason for enthusiastic participation is the fact that this topic concerns all of us. What kind of research should be done? But before that, let me come to HBNI as such. I could not attend the first day. I attended yesterday and today. And my thoughts were going back to 2003, when the proposal to set up HBNI was mooted. And I was interacting with the directors of all the CIs at that time. And I do recall discussions in Trombay Council in VARC. There was enthusiasm for this proposal, but there was skepticism as well. Both enthusiastic and skepticism, they were going together. There was some kind of skepticism about the success of this experiment. But today I'm very happy to see the way HBNI has come up, the way all the 11 constituent institutions, or we call NISER also as CI, they are functioning together, they are meeting together, and this meeting is a further reinforcement of the fact that all institutions are coming together and doing well. This clustering of R&D centers and grant-aid institutions is something which, in my view, can take us to a next higher level. The one example which always comes to my mind is that of Stanford University, where on the same campus, a research center operated by NASA exists, and leadership in the two is kind of interchangeable. Similar examples are there elsewhere at the global level, but in our country, this is the first example where we have brought together institutes. In Stanford, the NASA facility and the Stanford University, they are in the same campus, but here we are in different campuses. But in this era of internet, distances do not matter to the same extent as they used to matter earlier. I was very happy to see many remarks made by various speakers. Professor Panda spoke about sharing of resources. Gautam Bhattacharya again talked about coming together of all the institutions and again sharing resources. All these issues are very important. This really indicates that we have come a long way in the HBNI system. Yesterday, amongst the various remarks which were made by Dr. Anil Kakotkar, one remark was HBNI is doing very well, and I'm sure all of you have noted that particular remark. Title of this symposium is Discussion Meeting on Basic Sciences. So let us ponder the question, what kind of research should be funded? I think this is just, in my view, a question of nomenclature, and various kind of titles have been used by historians of science and technology. But I'll always recall in this connection what was said by William Shockley in his Nobel lecture in 1956. He said that the words like pure, applied, unrestricted, fundamental, basic, academic, industrial, practical, etc. are being used frequently in a derogatory sense. On the one hand, to belittle practical objectives of producing something useful, and on the other hand, to brush off the possible long-range values of explorations into new areas where a useful outcome cannot be seen. I think this is a very profound statement. Dr. Maity just spoke about how theory of relativity is used, let us say, we have a GPS system because of theory of relativity, how it's used to correct timing in various synchronized times, clocks on the various satellites. So nobody could have seen it, this kind of use, when theory of relativity was first given by Einstein. So both, all kinds of research are used. So I somehow, when it comes to nomenclature, I prefer to use the nomenclature academic research and post-academic research. Academic research which can be conducted easily in academic institutions. And for post-academic research, maybe one can divide that into early post-academic and final post-academic, where we need larger facilities, at times industrial scale setups, where either it has to be done in industry or in case it has to be done in R&D centers. But early post-academic research can be done even in universities and institutions. Both academic research and post-academic research generate knowledge that is necessary for national development. When examined from the perspective of national development, the pursuit of academic research alone, while necessary, is not sufficient. I think, I do not know how many of you follow the journal Issues in Science and Technology, which is available on the website of US National Academic Press. They published this kind of papers, and they had an issue published in winter 2020, where it was 2020 marked 75 years of publications of the report by Vannevar Bush, Science, the Endless Frontier, and that issue was discussed a lot. And argument was that the logic of STEP, Science, the Endless Frontier report written by Bush in 1945, the logic of the STEP is of the necessary but not sufficient sort. This was the conclusion of that set of papers, that academic research or basic research, whatever you want to call it, is necessary, but it is not sufficient for national development. Academic research will result into publications. Publications alone cannot lead to national development. It has to be, that research has to be followed up. Followed up by post-academic research such that it can lead to deployment. It's not that deployment will happen immediately. There are cases where deployment will happen after 100 years. There are cases where deployment of results may happen after 10 years. It depends upon case-to-case basis. So in my view, then academic research and post-academic research, that they are pursued together or in institutions which are closely related, chances of deployment are, the probability of deployment increases much further. So the government normally has to decide where to direct funding, to academic research or to post-academic research. There was a time when people like Einstein or Newton or Galileo, they didn't need any funding from the government. They were all funding resources required, but not something which were challenging the budget of the governments. Many a times, these people were earlier centuries, people were rich enough to fund research from their own resources. But now situation has changed. The organizations like CERN or ITER or LIGO or FAIR, the kind of resources which are needed are really very large. That is why several countries are coming together to fund research. So once the government has to decide what to fund, they will obviously, particularly in a country like India, they will try to give importance to post-academic research. I was talking to some colleagues on the sidelines of this workshop, and I just was trying to recall that the budget allocated to BRNS at some time, during 2007, 2008, used to be around 100 crores per annum. Now it's 30 crores. Now you factor in inflation and see to what extent it has come down, because the government has redirected priorities for funding. And this is something which we have to be very conscious about and try to say that how we proceed further so that we can make best use of the resources which are available to us. So what should be done by us in various institutions, whether R&D centers or grant in aid? we have to motivate research community to pursue at least early stage post-academic research. And for this purpose, a reward system that needs significant reorientation. The current system for rewards relies heavily on bibliometric indicators, despite the knowledge that publications alone do not lead to any development. Jerry Mueller, in his book, The Tyranny of Metrics, published in 2018 by Princeton University, argues that anything that can be measured and rewarded will be gained. Phil Beatty of Times Higher Education, the experts in ranking system, he writes, ranking should inform decisions and never drive decisions. I think this is very important. So we should look at what are the pressing challenges for our country: energy and environment, food and nutrition, water and sanitation, habitat, affordable health care, skill building and employment, and direct our effort in the direction where we can address these immediate challenges. And I find energy and environment to be most important amongst various challenges. At the Glasgow summit, the government has said that we will try to achieve net zero energy system by 2070. And this is a very, very onerous responsibility which has been taken by Government of India to really implement it on grounds. The resources needed in terms of funding, in terms of research efforts, in terms of social aspects which will arise, they are really enormous. And I don't think the implication of this announcement has really sunk in the research community. The full extent of this, I must say that all those people say in NISER, we have humanities and social sciences group, they have to direct their effort in this direction and try to develop expertise in the area of energy economics. Otherwise, something which will have real difficult time as we proceed further. Let me say that there is one more aspect which we have to keep in mind. In several meetings in which I participate, I hear words like, so-and-so is doing very well. One of his students is in MIT, one in Stanford, one in Berkeley. Nobody says that my student has joined DAE or Department of Space or Infosys or Tata Consulting Services. Why we have, after so many years of independence, still that complex that we tend to value a job in a foreign university more than a job, say, the way I have grown up in Department of Atomic Energy, I'll say this is one of the very good jobs we have. So we have to change our mindset and say that, and here I like to quote from a book written by Amartya Sen and John Dries. They ask questions: why are our first boys and first girls getting adopted by advanced economies? Do we need to encourage or discourage such adoption? Is the linkage of research priorities and curricula at higher education institutes to India's economy and needs very poor? The linkage is poor. They are asking, how do we improve that linkage? What India needs and what research institutions are doing. Emphasis on theory versus practice of building artifacts. What percentage of faculty has some industry experience? What policy framework can motivate the industry to employ highly qualified individuals who are coming out of our university system? This issue has to be tackled at both the ends, at the end of industry. They have to be motivated to employ highly qualified people, and also at the level of higher education institutions where they have to give full priority to internships. Internships by Indian students in Indian industry, so they are motivated to take up Indian problems. I think Dr. Kakotkar articulated the same sentiment in different words yesterday. So here, if you see the report on national education policy by Dr. Kusuri Rangan, he talks about the PhD students should be trained to become teachers also. Some kind of training should be given towards that end, but there is no mention of internships in that. So I feel that we know that all the students who graduate from universities in India will not find employment in academic institutions. A large fraction will be finding employment in industry, in the government, with NGOs, or they may have their own startups. So we must orient them in that direction as well. I often quote data from United States that only about 43.5% of STEM PhDs end up in academia. Remaining are not in academia. So that means if this is the kind of percentage in USA, ultimately as a number of PhDs increase in our country, same thing will happen here as well. So we have to train our students, those who are doing PhDs, that they should be equipped to join industry as well. So here I'll end up with two quotations. This is a topic on which I can talk and talk. The reason I got into this topic is the following. Maybe all of you who are in HBNI will be interested in knowing this. In 2009, a committee was set up by MHRD to examine deemed universities. When the report came, HBNI was placed in category B. Now, immediately, it was a shock to many of us. I was particularly shocked, and the membership of that committee is very renowned, and one has to convince them in a logical way as to what is the purpose of HBNI, in what direction we have to move. So I started reading all literature on the relationship between science and technology, on issues like academic research and post-academic research. Donald Stokes' book, which Dr. Kakotkar referred to yesterday, I read that book. I read on structures of scientific revolution and so on and so forth. And after equipping myself with all the knowledge in this area, again, drafted a long letter which was signed by Dr. Banerjee to one member of the committee. One more committee was appointed and appeared before that committee, made a new set of arguments to them, and indicated the importance of both academic research and post-academic research to proceed further. And the result was HBNI changed from B to A. It was a long struggle for me. Day and night I was reading this, and since at that time I was occupying various positions. After retirement from all those positions, I wrote down everything in the form of papers where I have expressed my views, which I learned during this process of learning. So I think now let me end with two quotations. One is Richard Courant. He is a mathematician who laid the foundation of the finite element method, which all engineers, all physicists, I think maybe people from other disciplines also use. He opined that to pursue mathematical analysis but turn back on applications implies subjecting analysis to hopeless atrophy. Essentially meaning look for application, and I do get a feeling from the presentations here that everyone is looking for application of research, and this was said by Richard Courant. Then there's a book, The University in the 21st Century by Elkanah and Klufer from Germany, written in 2016. They write the fact that hundreds of students on new universities in China and India copy the curricula from the United States or Europe and send many of their doctoral students to study there results in a serious neglect of their own scholarly traditions as well as local and regional problems. Since working on such problems seldom receive proper recognition, a focus on them usually does not help in building a scholar's career. Hence, reorienting the system of incentives is the key to real challenge. So while we should interact with all other countries, definitely spend postdoctoral fellowship tenure in other countries, but still our feet should remain grounded. We should concentrate on problems that are of immediate interest to our country. And this can be done only by leaving equal emphasis on academic research and post-academic research and pursuing them in a synergistic manner. Thank you.
Thank you for your invaluable message, sir. Finally, I request Professor A.K. Dureja to propose the vote of thanks.
Good afternoon, everyone. It's my great privilege to propose vote of thanks. First of all, let me thank Professor Grover for taking out his time from his busy schedule. It was indeed our pleasure to have you here, sir. We have made note of points illustrated by you. On behalf of HBNI, we want to thank Sri Vyas, Chairman AEC and Chairman Council of Management HBNI for always encouraging us to move out, to come out with original ideas and support us to execute this. We are thankful to our Chancellor, Dr. Kakotkar, for guiding us to achieve these targets. I am personally thankful to our Vice-Chancellor, sir, and Dean, sir, for creating enough opportunities for us to organize such events. This meeting is just a kickstart of many more meetings for collaborative work among various CI, OCC of HBNI. We are grateful to all the directors of various CI, OCC who enthusiastically participated in this program and given their full support for the collaborative activities and deliberated as session chairs. Thank you so much, sirs. I'm sure this interaction will definitely take the whole family of HBNI to a higher platform. We are thankful to Director BRC, Controller BRC for all the support for arranging this meeting. We are thankful to Professor A.K. Tyagi, Professor S.M. Yusuf, Professor Tiwari, and Professor S. Kannan for extending help in managing many things. We are very much thankful to all the speakers for sharing the details of facilities available in their institutions and discussing about the frontier areas of research for collaborations. We are thankful to Director TMC, Professor Banawali, and other faculty members of TMC and ACTRAC for arranging a wonderful evening. We are very much thankful to Professor Maity for putting his wholehearted effort to make this event a grand success. We are very much thankful to all the members of various committees who work tirelessly to discharge their associated responsibilities in a very responsible manner. We are thankful to all the dignitaries in this hall and available online for accepting our invitation and sparing your valuable time. This event would not have been a success without the active support of all the staff members of HBNI who directly or indirectly helped us in arranging this discussion meeting, the staff of DI Convention Center, SIRD staff members, Transport Section, BRC, Sign Caterers for providing the food, Mr. Ali and his team for videography and photography, Mr. Vinod for ID hardware support, DCSM Security and Shriram Travels. The technical support provided by Computer Division BRC, especially Shri Rohita Sharma and ECL colleagues, was wonderful and we thank them all. Lastly, I want to thank our compare of this discussion meeting, Ms. Karunya Dei, for excellent coordination and management. Thank you so much, Karunya. The meeting gave us an opportunity for a lot of interaction among participants formally and informally. Thanks to all the participants to make this event a grand success. Thank you all.
Thank you, sir. On behalf of HBNI, I sincerely thank the directors of CI, speakers, and participants for their contribution and participation. Lunch has been arranged at the cafeteria for everyone. After this, I request the delegates who will be visiting VRC to please board the bus at the entrance of the convention center, which will take you to the training school. You may leave your phones and electronic gadgets there and proceed to board the bus, which will leave to VRC early as possible. Thank you, everyone.